my screen. Okay, so I will share my screen. I think you can see my screen.
Yes, sir, we can see.
Okay, so today we have this second talk in our series, that is seismic design of buildings using NBC 105/2020. And this talk is about ductile detailing. So the first talk we had was regarding calculation of forces. So once you calculate the forces, you can perform analysis and then you can perform design. After design, you have to take up detailing. So what provisions are there in NBC 105 regarding detailing? We are going to discuss that, and we will also have a comparison of those provisions with those given in IS 13920. So I can tell you that in NBC 105, there are some improvements above 13920. So there are few problems in 13920. Some of those problems have been improved in NBC 105, and I will tell you that wherever that improvement is. So in ductile detailing, the role of ductility in seismic resistance of any structure we discussed in the last talk. So considering the equal displacement principle, we can see that the response reduction factor which we get is equal to the ductility capacity of the building. So we take advantage of ductility in dissipating energy, and by virtue of that dissipation of energy, we can reduce the force for which we are going to design our structure. So how to ensure that that much ductility capacity which we have taken advantage of is available in our structure? Then only the structure will be able to survive under that reduced earthquake. So what is the source of ductility in our structure? So source of ductility in our structure is from the material. In RCC structures, we have two materials, concrete and steel. So we should have the appropriate material. So codes provide criteria for selection of material. In case of concrete, the code says that it should be more than M20 grade concrete. That was there in IS 456 for long. And this M20 criteria actually came from ductility, not from ductility, it came from durability. So to avoid the corrosion, so that the concrete is not very porous. So that M20 criteria was given. So for buildings more than 12-meter height, NBC says that we have to use M25, a higher grade concrete, so that when the axial force is increasing, we get sufficient ductility. Then steel is very important because the ductility is actually coming from steel. It is the steel which is providing the energy dissipation capacity to RCC structures. So up to Fe415, there is no issue. We can use Fe415, but recently it must be in Nepal also. In India, it is now very common to use Fe500 and 550. Fe415 is also not used. The advantage is clear because if we are having higher tensile strength, the amount of steel required will be less. But there is an issue, and that issue is that if I look at the stress strain curve of steel here, we can see that as the grade of steel is increasing, the ductility goes on reducing. So that's why there is an upper limit on the grade of steel. Not more than 550 is currently allowed, and it should be ensured that the steel which we are using is having total elongation, that means ultimate strain more than 15%. So if the strain, ultimate strain is less than 14.5%, then that steel cannot be used in seismic areas, and Nepal as well as India, both are seismic throughout. So we cannot use any steel which is less than 14.5% total elongation. So when we are testing the steel, we have to look not only for the strength, we have to also look for the ultimate strain or total elongation. Then another criteria is that the expected steel strength or ultimate strength of steel should be at least 15% higher than the yield strength. Ratio of ultimate strength to yield strength should be 1.15. What does that mean? It means that there has to be significant strain hardening. So there should be strain hardening. After yielding, it should not become flat. It should have the strength increasing by 15%. What is the purpose of this? Larger is the overstrength ratio, strain hardening ratio, more or longer steel will be involved in plastic hinging, in yielding. So larger length of a steel bar is going to yield, and larger length of steel is going to yield, then we will get larger rotational ductility. For the same level of strain, the curvature ductility we will get same, but the rotational ductility is depending on the curvature ductility and the length of the member which is yielding. So length of the member which will experience yielding of steel will depend on this ratio. That's why a minimum ratio of 1.15 is given in both the codes, NBC as well as IS code. So almost same conditions are given in IS 13920 also. Sorry, this is not 1893, this is 13920. So these are given in 13920 also. Now, if we look at the stress strain curve of concrete, we see that concrete, as we increase the grade, becomes relatively brittle. And as compared to steel, this is much brittle. So the peak occurs something close to 0.002, and the failure occurs somewhere in between 0.003 and 0.004. So in our code, we take it up to 0.0035. So if I take 0.0035, then the ductility ratio I'm getting is less than 2. So in case of concrete, the ductility ratio is less than 2, which is very low. That's why concrete is a brittle material. On the other hand, in steel, minimum was 14.5%, and the yield strain is something like 0.125. So here we are getting the ductility ratio of more than 100. So that much ductility is available from steel, more than 100, and there we are having 2. So we can understand how much more ductile steel is as compared to concrete. But if we look at the failure of concrete, we understand a property of concrete which is very important to us. For example, you must have tested cube and cylinders. We know that cylinder strength is lower than the cube strength. Why? Why the cylinder strength is lower than the cube strength? If I take the same material, same batch of concrete, make a cube and a cylinder, the dimension of the cube is 150 by 150 by 150 mm. On the other hand, the cylinder has a diameter of 150 millimeter and height of 300 millimeter. So height to diameter ratio is more in cylinder as compared to cube. So what happens when this concrete is subjected to compressive stress in vertical direction, as I have shown here, due to Poisson's effect, it is subjected to tensile strain in the transverse direction. It is a simple phenomena. If you press something, any object you press, it will try to conserve its volume, and when it is compressing in the vertical direction, in the horizontal direction, it will try to expand. And when it is trying to expand, it is in contact of the machine plates, the compression machine plates at top and bottom. And this is the friction between the plates and the concrete cube. We get friction, and that friction prevents movement of this plate, this cylinder or cube outward. So we get a sort of confinement at the ends, and as a result, we get the cracking pattern like this. So this end friction effect, which is giving the confinement to the concrete at the ends, this continues roughly up to 0.8 times the diameter or 0.8 times the cube dimension below. So in case of cube, we can see 0.8 from the below, 0.8 from the top. Whole height of the cube is affected by end friction effect. Whereas in case of cylinder, 0.8 from the top, 0.8 from the bottom, and still you see in the middle there is a height of 0.4 times the diameter, which is free from end friction effect. So it is the cylinder strength which is near to the reality. The cube strength is artificially increased because of this end friction effect. And that's why when we are doing our designs, so you remember in calculating the concrete strength, we are using a factor of 0.8 and another factor of 0.85. So this 0.8 factor and 0.85 factor, which multiplied together gives us 0.67. And 0.67 we divide by factor of safety of 1.5 and we get 0.446. So here one factor corresponding to end friction effect is included, which corresponds to the error in testing of cube. That error is not there in the cylinder. Okay. Then you may ask that why don't we test the cylinder? Let's test the cylinder because cylinder strength is more realistic. The problem in cylinder is that when you are casting the cylinder, the top surface of the cylinder, and that is there in case of cube also, is not smooth. That is undulating. And if you will test it in the same position as you have casted it, there will be concentration of stress. Non-uniform stress will be applied on the top surface. So in case of cube, you can do one simple trick. You can just rotate it, and so that the vertical faces become the horizontal face, and those faces are parallel as well as smooth. On the other hand, in case of cube, or in case of cylinder, if you have to test it, you have to do capping. So you have to use either molten sulfur or gypsum plaster, or you have to grind the top surface smooth and parallel to the bottom surface, so that the distribution of stresses is uniform. We don't get stress concentration, and this takes time. This requires effort. That's why the cube test continues in both of our countries. We test cube, and we use a correction factor of 0.8 to convert cube strength to cylinder strength. Then the other factor 0.85, that is the factor due to size effect, because the size of the concrete, the volume of the concrete in actual structure is much larger than the volume we are using in even in a cylinder. In cube it is even less. So even when we are testing cylinder, then the volume of the concrete is less, and chances of a weaker section in that volume are less as compared to the real volume which is there in the structure. And as a result, the cylinder strength is also higher than the actual strength of the concrete in structure. So we have to apply a correction factor for this effect also, which we call size effect. So due to the size effect, there is a factor of 0.85. The strength in a member is approximately 85% of that of the cylinder, and cylinder is 0.8 times of the cube. So if I'm using FCK, which is based on cube strength, I have to multiply that by a factor of 0.8 and 0.85. That becomes 0.67 FCK. And that's how this 0.67 FCK comes. And there is no factor of safety in this 0.67 FCK. This is only the corrected strength. Factor of safety is applied over and above that. So that is 0.67 divided by 1.5, which becomes 0.446. So that is used in our calculations. Now think of another test which you might have done, which is split cylinder test. So a split cylinder test is done to determine the tensile strength. Although we are applying compressive strength, but this is failing in tensile action. Why it is failing in tensile action? Because of the Poisson's effect. And here, because the contact between the cylinder and the plates is a line contact, a point contact, and this point contact continues along the length of the cylinder. That's why I'm calling it line contact. So the contact area is very, very small, and because of that small area of contact, the friction is not mobilized. So we don't have any confinement due to end friction, and as a result, the cylinder fails by splitting. Why the cylinder fails in splitting? Because the tensile strength of concrete is very less as compared to the compressive strength. For example, the Poisson's ratio in case of concrete is close to 0.15. So Poisson's ratio is 0.15, but the tensile strength is only 10% to 12%, 0.1 to 0.1 to 0.12. So before failure in compression, the failure occurs in tension due to Poisson's effect. Now imagine this cylinder was made of steel, although it will be difficult to test when we have a cylinder of steel. But suppose I was testing a cylinder of steel. Do I expect that also to split? No, that is not going to split. Rather, that will yield, that will flatten. It will become a plate if I press it. Okay, but that is not going to fracture in tension. Why? Because the tensile strength of steel is as high as its compressive strength. So Poisson's effect will be there. There will be tensile stress, but it is not going to fail. Its capacity is much more than. So taking cue from here, let's test a cylinder, concrete cylinder, which is encased in a tube. So this is a steel tube all around. So I have encased this cylinder inside this tube. And then I am trying to test it. Can you imagine what will happen? Will it fail in the same manner as the cylinder earlier by splitting, by diagonal cracks, vertical cracks? Will it fail in the same way? No. What will happen? When I subject it to compression, it will try to expand, and the sleeve which I have provided all around this tube I have provided, this will be subjected to hoop tension. And as a result, it will apply a confining pressure on the concrete. And this confining pressure is radial compression. So when I apply the compressive stress in the radial direction, opposite of that will act. So due to Poisson's effect, it is in compression. So tensile stress will act in the vertical direction, and this tensile stress will partially compensate the applied compressive stress. And what will happen when it is going to fail? This cube will not fail till this tube ruptures. Under the hoop tension, when the sleeve will rupture, it will fail. So here the concrete has changed from unidirectional, uniaxial stress state to triaxial stress state. And you know, if a material is subjected to triaxial state, it does not fail. It will fail only when the deviatory stresses, and deviatory stresses are the difference between the horizontal and vertical stresses. So it fails because of the difference of that. So till this confinement is available, it is not going to fail. And when it will fail? When the confinement is lost. And confinement will be lost due to rupture of this steel sleeve, which I have provided around this cylinder. So this sleeve governs the strength and strain in the concrete, which it can take. And as a result, the stress strain curve of confined concrete, you can see, is enhanced tremendously as compared to unconfined concrete. So what we see here, this is the unconfined concrete. This white curve is unconfined concrete. It fails somewhere between 0.003 to 0.004. But the confined concrete, you can see the strength has increased. FC dash is the cylinder strength. FCC dash is the confined cylinder strength. And it continues. And where it will fail? It will fail when the hoop or the sleeve fails. In real structures, we cannot provide sleeves. We do not provide sleeves. But what we do, we provide stirrups. And those stirrups provide the confinement. And when the concrete is going to get crushed in under earthquake or under any other loading in compression, when the hoop will rupture, hoop will fail. So we have to understand that this transverse reinforcement, this is the key of concrete ductility during earthquake, and its failure will govern the failure of concrete. Suppose I have not properly anchored this hoop, then what is going to happen? Before rupture, it will open out at much lower force. It will open out and the confinement will be lost and the concrete will fail very quickly. So that's why this anchorage of this stirrup into the core concrete is very crucial. All the codes talk about this. So if I consider different types of confining pressures, and the behavior of concrete, we can understand from these curves. So this lowest one is the unconfined concrete, and the top one is the hydrostatic pressure. So if I apply hydrostatic pressure uniform from all the sides, then I'm going to get a stress strain curve which is more or less flat. Then if I'm using spirals, in case of circular columns, we can use spirals. So if we are using spirals, then I will get close to hydrostatic pressure. Although there will be some degradation because spirals are not confining the concrete continuously. If I'm using circular ties or rectangular ties, then I will get a curve like this. So here the confinement is not that good as we are getting in case of spirals or in case of hydrostatic pressure. But still, the strength and ductility increases significantly as compared to unconfined concrete. So this ties, the transverse reinforcement is very important for achieving ductility in my structure. Now, if I am considering a circular section where circular hoops or spirals are provided, then we can see that the full length or perimeter of this spiral or circular tie will cause confinement to the concrete. So radial stress will be applied all along. Okay, and whole of this white portion, the core concrete, will be confined. On the other hand, if I have a square section like this, then what is going to happen? Due to Poisson's effect, when the concrete is trying to expand outward, this rectangular hoop, this leg of this rectangular hoop, this will bend outward and it will try to become circular. Okay, because then only it can resist the radial pressure by axial load. So the shape of this circular section is such that if we are applying a radial pressure, it is causing only tension. No bending is there in this circular section. There is only tension. And our bar has very little strength in bending, but it has good strength in tension. So it will try to achieve a circular shape by bending so that it can resist this radial pressure. So when it is bending, the confinement in the central portion will be lost. But one thing we see, the corners, whether it is circular or it is rectangular section, square section, the corners will remain in place. So these bars in the corners, these longitudinal bars will not be allowed to move. And as a result, the confinement will come from the longitudinal bars. And similar way, if I can prevent the movement of longitudinal bars in the middle in outward direction, then I can provide confinement through these longitudinal bars also. And in between, the confinement will be available through arching action. So full core will not be confined, but this white portion of the core will be confined. If I want to enhance the confinement of the core, I should have more number of longitudinal bars which are restrained against movement in outward direction. Then these longitudinal bars are confining. Okay, so here in the right hand side figure, you can see that we have increased the number of bars, and you can see that the relative area of this white portion of the core, which is intact, has increased as compared to this. Here there was more shaded area. Here the shaded area has reduced. So confinement has improved. So to improve the confinement, the key is to provide as many longitudinal bars as possible. So I should not provide large diameter, few longitudinal bars. Rather, I should provide several longitudinal bars, maybe of a smaller diameter. And then I should provide the arrangement of the ties and stirrups in such a way that maximum number of bars are restrained against movement in outward direction. Then the confinement will improve and the ductility of concrete is going to improve. So here in this curve, a comparison between different arrangements of stirrups has been provided. So you can see that in first case, there are 8 bars, longitudinal bars, which are restrained. In the second case, you have 12 bars, which are confined. In D also, B and D have equal number of bars, but the arrangement of stirrups is different. In B and D, the arrangement of stirrups is different, but the number of longitudinal bars provided at the perimeter are same. Here, if you look at this, then the number of bars are increased further. Here we have 16 bars. Okay, so 5 and 5, and then 6 bars in between. So 16 bars on the perimeter. There are some bars in the middle also I've shown, or I don't know whether it is because of the drawing or these are the bars also provided. So definitely the maximum number of bars, longitudinal restraint bars, are in C. And you can see here the best performance is given by C. The best confinement comes from the arrangement C. Arrangement B and D, these are giving more or less same stress strain curve. So you can see B and D, there is not much difference. B and D are more or less same. And A has the worst performance. It is having the minimum confinement available. So you can see that the confinement, the key to the confinement is longitudinal bars, and those longitudinal bars should be connected with stirrups or ties so that these do not move outward. This is the basis of ductile detailing in all the codes. So when we will discuss in successive slides the provisions of the code, we will see that this is the basis of those provisions. Then along the length of the member, we provide stirrups at some spacing. We do not provide continuous confinement. The confinement is provided at the level of this hoop or stirrup. So there the confinement is available in the full width, but as we go towards the middle between the two transverse stirrups, we can see that again the confinement goes on, the effect of the confinement goes on reducing, similar to what we had in case of compression testing, the end friction effect. So end friction effect reduces as we go away from the end. In the same way, the effect of the confinement reduces as we go away from the stirrups. So in the middle between two stirrups, the confinement effect of the confinement will be minimum. So to avoid that, what we have to do, we have to provide these stirrups close enough. So these stirrups should be closely provided, especially at those locations where I'm expecting my member to yield, where the concrete will be subjected to large strain. So there these stirrups should be close enough. How much close? That is given in the code. Okay, so let us see what are the requirements in NBC 105. First requirement is regarding this anchorage. So this anchorage should be properly made here with 135 degree. If I leave these at 90 degree, you can understand when it will be subjected to compression, whether it is bending or whether it is axial force and bending. In both the cases, concrete will be subjected to compression. And when concrete is subjected to compression, it will try outward, it will apply outward pressure. And under that outward pressure, these steel stirrups and ties will be subjected to tension. And if these are not properly anchored, these will open out. And as a result, the confinement will be lost and the ductility will be lost. So what the code says, that we have to anchor these stirrups like this, and this anchorage should be at least 6 times diameter and not less than 65 millimeter. Okay, so that is one thing which we have to look at. The second thing we have to look at is that the two bars, longitudinal bars, which are restrained against moving outward, the spacing between these bars should be less than 300 millimeter. So any two bars, any two adjacent bars which have been restrained against movement outward should have a spacing not more than 300 millimeter. Okay. Now this error is there in Indian code and it has been taken in Nepalese code also. It shows that the tie has to go outside the longitudinal, outside this stirrup. That is not needed. Okay. Because what is the purpose of providing the tie and this stirrup? The longitudinal or the longer leg of the stirrup in any case is going to bend. It will bend in the circular fashion. It will try to achieve a circular shape. but the longitudinal bars which are provided at the corners, those should not move. So that purpose it will satisfy. Then here what we are doing, here the purpose of tie is to prevent the uh, movement of the longitudinal bar outward, not the bending of the longitudinal bar. That is not needed. So this is not needed for confinement. And what is the problem if we provide? The problem is loss of cover, because the cover will reduce. Why I am saying that it should not be done? Because if somebody is doing this, it should be good. So one thing is that it is difficult. It will be difficult to provide. That is one problem. The other problem is that the cover here is going to reduce, because the cover on the tie will be less by the diameter of the system, and the chances of corrosion will increase. The chances of decay of this tie, okay, degradation of this tie due to corrosion will be more, and maybe it is not available at the time of earthquake. That's why I will recommend that this tie should go around the longitudinal reinforcement only. There is no need to engage the long lag of the transverse stirrups by this tie. That is not needed. Only thing is that the distance between two longitudinal bars which are restrained either by tie or stirrup should not be more than 300 millimeters. That we have to follow. Okay. Then these stirrup arrangements, how we can provide. So these can be either in the form of closed stirrups or closed stirrups and ties, or sometimes it may not be possible to provide a full closed hoop. In that case, a U-shaped stirrup and a tie is permitted by the code. It is permitted by Indian code. It is now permitted by NBC also. But definitely the efficiency of this will be less than efficiency of this. So it's better to provide this arrangement than this arrangement. But where it is difficult, where you are not able to provide due to any region, then you should go for this. Okay. And the requirements for this stirrup are also given here. Now, at which location we have to provide this closely spaced stirrups, what we call a special confining reinforcement. This special confining reinforcement is to be provided at the locations where we expect our members to yield. We are expecting the concrete to develop large strains. There, the confinement is important. And I told you that the confinement, this transverse reinforcement is also important to support the longitudinal bars. That's why it is also important that we provide larger number of legs in our transverse reinforcement and try to restrain each and every longitudinal bar, so that under buckling, it is not subjected to low cycle fatigue. The failure does not occur due to low cycle fatigue. So it will be good if we can support each and every longitudinal bar using hoops and ties. If we arrange that way, it will be better. Now, at which locations we are expecting yielding? The yielding we are expecting where the maximum bending moment is occurring during earthquake, and that is occurring in beams and columns both near the joint. So this special confining reinforcement is to be provided near the joint in the beams. So in the beams, it is to be provided in a length of 2D, where D is the depth of beam. So this is the depth of the beam, effective depth rather. So in 2D, we have to provide this. And these are the closely spaced stirrups. Area of these closely spaced stirrups and their spacing has to be calculated as per the code. Okay. And the first stirrup here should not be at a distance greater than 50 millimeters. So it should be close to the face. The first stirrup, which is confining the concrete, should be as close to the face as possible, not more than 50 millimeters in any case. Now, 2D from this side and 2D from this side is to be confined. In between, the special confinement is not required. We can provide the normal shear uh, reinforcement and the normal confining reinforcement, which is as per the concrete design code. Okay, IS 456 in Indian condition. Now, these stirrups which we are providing here, their spacing is governed by these three conditions. D by 4, 8 times the diameter and 100 millimeter. Usually 100 millimeter is going to govern, or 8 times diameter. 8 times diameter is coming because of the buckling of the longitudinal reinforcement, because longitudinal reinforcement will be subjected to alternate compression and tension. So it does not undergo excessive buckling and then rupture. To avoid that, the spacing should be maximum 8 times the diameter of the smallest bar. So whichever is the lowest diameter of the bar, 8 times of that. It should not be more than that. Suppose you are using 10 millimeter longitudinal bar. Okay, 10 millimeter is much smaller bar for a beam. Generally, we do not use. But suppose I take example of a 10 millimeter bar, then the maximum spacing can be 80 millimeter, not more than. And it should not be more than 100 millimeter in any case. So that is there. And it is to be provided in this length 2D. In addition to that, the code also has the limitation on longitudinal reinforcement. So there is limitation of minimum longitudinal reinforcement. There is limitation of maximum longitudinal reinforcement. So minimum longitudinal reinforcement, as you can see in this slide, as per NBC, it is 0.24 under root FCK divided by F5. And the maximum longitudinal reinforcement is 2.5%. Actually, 2.5% is also on higher side. So generally, we keep it much lower so that there is no congestion. We can do the concreting easily. Okay. In addition to that, there are more requirements. And those requirements are, I will explain here, that at any section, okay, the reinforcement at top or bottom should not be less than half of the reinforcement at the other face. For example, near the joint, we know that at the top we get very large reinforcement because the earthquake force and the gravity force both cause the moment such that the tension is on the upward face. So here the bending moment due to earthquake and dead load and live load gets added, whereas in the bottom reinforcement, when the reversal of earthquake occurs, we have the bending moment causing tension due to earthquake here. The gravity load will always cause tension at the top face. So the net moment at the bottom face will be much less as compared to the net moment which is causing tension at the top face. So usually the tension reinforcement at the top will be much more than that at the bottom. But code says in any case, the bottom reinforcement should not be less than 50% of the reinforcement you have provided at the top. Even if it is not needed 50%, you have to provide it minimum 50%. Why? The reason is that if I'm having too much reinforcement on compression face, so this tension reinforcement, which for one direction of earthquake will act in tension, the top reinforcement, for the other direction of earthquake, it will act as compression reinforcement. And when it is acting as compression reinforcement, and it is much more than the reinforcement on the other face, which is acting as tension reinforcement, the depth of the neutral axis will be very shallow. The neutral axis will be at very shallow depth, very close to the top reinforcement. And in that case, a small strain in concrete due to the strain compatibility will cause very large strain. We assume a linear distribution of strain. So very large strain will occur at the bottom steel. And it may happen that the bottom steel fails, ruptures much early because of this large strain, excessive strain. That's why the code has said that the reinforcement at any face should not be less than half of the reinforcement at the other face. So that is also important. Now, exactly same provisions are there in IS 13920 also. So I will skip those. Now, in case of columns, similar to beams, we have to provide a special confining reinforcement in columns also. And here you can see that in this length, L0, near the beam soffit and beam top, here L0 from the beam face, this is to be provided with special confining reinforcement. And here, in case of columns, the requirement is even more stringent because it is subjected to a combination of compressive force and bending moment. So first of all, this length L0, this should be larger of these three, either 450 mm or the largest sectional dimension or the clear length divided by 6. So that much is to be provided. So the largest sectional dimension, if this dimension is D, so this should be larger of D, L by 6 or 450 millimeter, whichever is higher. And then the spacing of the confining reinforcement in this case is governed by 6 times diameter. In case of beam, it was 8 times diameter. Here it is 6 times diameter. Okay. So it should be lower than 6 times diameter. The dimension, the lower dimension divided by 4. So whatever is the lower dimension of column, that divided by 4 or 100 millimeter. It should not be more than 100 millimeter. Okay. And the area of the cross section or the bar of the hoop, which is making hoop, area of that is governed by these equations. Okay, so in case of circular hoops, similar expressions are given in case of rectangular hoops also. Now here you see ASH is directly proportional to H. Okay, so here SB is the spacing. So let us say it is 100 millimeter, we keep. So then it is FCK and FY are constant. AG by ACC. ACC is the confined concrete, core concrete, and AG is the gross area. So capital B by capital D will be AG. And when you remove the cover, then it becomes ACC. So AG by ACC, FCK by FY, these are all constant. SV, let us say a given spacing we have taken that is constant, then we can say SH is proportional to H. What is this H? H is the spacing between the adjacent longitudinal bars which are restrained against movement. Okay, so here it is written longer dimension of the rectangular hoop, but that doesn't explain it fully. Okay, if you have provided ties, then also this H will reduce. So this is actually the spacing between these longitudinal bars which are restrained. So if you are having more number of ties which are restraining the closer bars, or the spacing between the restrained bars is reduced, then ASH is going to reduce. Okay. If you were having only rectangular hoop, then what is given here is okay. That is enough. But when you are giving ties also, then this is not enough. Please keep in mind, it is not the longer dimension of the rectangular hoop, because it is written here not greater than 300 millimeter. It has to be less than 300 millimeter. So actually what it is referring to is the spacing between the longitudinal bars when the ties are provided. Okay, exactly same provisions are there in Indian code also. Now, if we compare with ACI 318, we can see that actually in ACI 318, the provisions are much more advanced. Okay, there it depends, the area of the hoop depends also on the axial force. So when the ultimate load is less than 0.3 Ag by Fc dash, then there is one expression. If it is greater than 0.3 Ag Fc dash, then it is another expression. It also depends upon the compressive strength of the concrete. So the Fc dash is the cylinder strength. So for normal concrete, Fc dash less than 70 millimeter, there is one expression. For cylinder strength more than 70 MPa, also we have to consider this C also. So this will be governed by C also. And in case of high strength concrete, we have to provide more confining reinforcement. Okay, and it also takes into account the number of longitudinal bars which are supported by the link, the arrangement, and this factor Kf. Okay, Kf and Kn, they are appearing. So this factor Kf, this takes into account the strength of the concrete also, which are missing in Indian and Nepalese code at the moment. Perhaps the understanding is that in our countries, we are still not using concrete greater than 70 MPa. 70 MPa is very high strength concrete. That type of concrete is not used in our countries. So means what expressions are given are okay. But in case in some project, if you are using compressive strength greater than 70 MPa, you have to use these expressions. Those expressions are not valid. Then similar to the beam column joints, the joint of the columns with foundation will also be subjected to large moment and hinging will occur. So we have to provide special confining reinforcement there also. And that special confining reinforcement has to continue into the foundation for a length more than 300 millimeter. So for 300 millimeter length, it will be this special confining reinforcement will continue into the foundation also. So that here we get good ductility. And all our buildings, we will see later, we will design in such a way that the beam sealed first, then the column sealed at the foundation. Okay, so foundation is also a potential location where the plastic hinge will take place, and we have to carefully detail the column reinforcement inside the foundation. Okay, identical figure is given in IS 13920 also. Then a new command, a new provision which came in IS 13920, and it has been taken with taken in NBC also. This is important, and it is actually controlling the anchorage of the beam reinforcement into the column. So you can see that, suppose I take the interior joint first. So what is going to happen when it will be subjected to earthquake? Then this beam will bend. Let me use the pen, then perhaps it will be clearer, because this is an important topic. So I want you to understand that. So during earthquake, what will happen? This beam will be subjected to bending like this. This beam will be subjected to bending like this. Both of the beams on left side and right side are subjected to moments in the same direction. If reversal occurs, then this direction will change. But for one given direction of earthquake, both the beams will be subjected to the same moment, either clockwise and anti-clockwise. And due to that, what is going to happen? We will have tensile force in the bottom, compressive force at the top. Here, we will have tensile force at the top and compressive force at the bottom. Now you can see in the bottom bar, both the moments are applying force towards right. So here, large shear force will act in this direction. Here, large bond stress is going to occur here. And if this dimension of the column is not adequate where the anchorage is provided, this bar will slip inside the column. Okay, that's why there is a requirement of 20 times diameter on this depth of the column. This should be greater than 20 times diameter. Same is applicable here. Okay, this we will talk later. There are more issues here, we will talk later. But for an interior column, what we have to ensure is that there should be adequate anchorage of the beam reinforcement into the column, and for that purpose the column dimension has to be sufficient. So one limit on the column dimension is coming from here, this 20 times diameter. Another limit we are getting 300 millimeters, so it should not be less than 300 millimeter. Earlier code it was lower, so it has been increased. Otherwise people were giving very thin columns, and those thin columns which were having one dimension very low and the other dimension very large, what we were calling in commonly in our industry as blade columns. So that type of columns are also not permitted. The width to depth ratio should be greater than 0.45. So we cannot have a column in which one dimension is very large as compared to the other. The ratio of the two dimensions should be of the order of 2. Okay, 0.45. So 1 upon 0.45 is close to 2. Okay. Then anchorage of the longitudinal reinforcement of beam into the column is also a big problem, because what will happen when it will be subjected to bending moment like this reinforcement will try to slip, and it is a cyclic loading. So in the next cycle, the direction will change, and again, several cycles will be applied there. So slowly, this bar will try to come out. So this bar should be properly anchored into the column. And here, let me tell you that in NBC, there is an improvement over IS 13920. What is given in IS 13920 is this length has to be LD plus 10.5. Okay, you remember in Indian code IS 13920, it is LD plus 10.5, and this LD plus 10.5 becomes much larger. And what you have to do, you have to take this longitudinal reinforcement of the beam into the column to large depth, and this causes some construction problems. So it is difficult to provide. So that has been improved in NBC, and in NBC this detailing has been taken from ACI code. And here the anchorage length consists of two parts. One is this horizontal part and another is this vertical part. So vertical part is only 12 times the diameter, so which is not very large. So even if I'm using, let us say, 25 diameter bar, so this will be roughly 400 millimeter. Okay, so it is possible to manage. The LDH is what we call the horizontal development length, and the expression for LDH is given. And this LDH, if you calculate for, let us say, FCK is equal to FCK 40 MPa and F by 500 MPa, this comes out to be roughly 16 times diameter of the bar. So 16 times of the diameter and 12 times of the diameter, that becomes 38. No, not 38, 28 times the diameter. So it is requiring only 28 times the diameter, whereas in Indian code, it is requiring LD plus 10.5. So 50 times diameter plus 10 times diameter, roughly 60 times diameter. So 60 times diameter is required. So this is very, very long. Okay, that is not needed. This much is not needed. Okay, only thing is that the NBC is saying that this 16 times diameter has to be straight. This you cannot achieve by bending. So this straight bar has to go into the column up to LD or up to the face of the longitudinal bar, because another limit is given here. LDH should be greater than DC minus concrete cover. What does that mean? DC is the depth of the column minus cover. So that will become the location of these longitudinal bars. So this bar has to go to the same plane in which these longitudinal bars are provided. Why? That is because when this bar will be subjected to tension, it will try to open, and there will be a diagonal shear force developing in the joint. So this bar will try to open. So it should be restrained by the horizontal reinforcement which we are providing, the transverse reinforcement which we are providing within the joint. So that's why this should be restrained by the same transverse reinforcement which we are providing. Okay, so alternative way is, if I cannot accommodate LDH within the column, I can provide a stub beam here. So I can provide a stub where this reinforcement will go here, but note this reinforcement. This is important. So that's what I was talking, that when it will be subjected to diagonal shear, this will try to open. To avoid that opening, this reinforcement is to be provided. Okay, so this horizontal stirrups, these are important. These are to be provided if I am using this stub arrangement to anchor the longitudinal reinforcement of the beam. Now, in this case, what you are doing, this bar is inside the core. Okay, it is inside the transverse stirrups which we are providing in the joint portion. So that will take care of its opening. It will not allow it to open. Okay, so in Indian code, this LD plus 10.5, that becomes difficult to provide. Then the beam column joints needs to be checked for shear force. So first we have to calculate the shear demand, the shear force demand. Shear force demand in an interior column can be obtained like this. So this is the demand VJH. This is the horizontal shear force in the joint. This is the expression given. Now you can understand why AST1 and AST2 is there. That you can understand from this figure. So when I'm applying, or maybe even better understood here. So I have a shear force equal to VC, which is acting here. In the joint, what I'm getting? I'm getting the shear force. Actually, if earthquake is causing anti-clockwise movement, the column shear will be opposite in this direction. What I have shown. Okay, so this will be the shear force in the column VC. Now, the shear force which will be acting here will be equal to this tensile force, okay, and this compressive force. So tensile force and compressive force which are acting here, you can see this compressive force you can take as this tensile force, because in beam C has to be equal to T. Then whatever is coming from here, this is compressive force and this is tensile force. So compressive force will be actually acting in the reinforcement as well as in concrete, and here also we can take C equal to T. So what this shear force in the joint I am getting, Vj, this is equal to the T1 from left side and T2 from the right side. Actually it is C2, T1 plus C2, but C2 is equal to T2. So T1 plus T2 minus this shear force which is acting in the opposite direction, VC. So that is the expression which is given in the code. EST1 into Fy. What it is giving? It is giving us T1. Fy into EST1 is T1. Fy into EST2, that is T2. So T1 and T2 multiplied by 1.25. Why this is multiplied by 1.25? To consider the effect of strain hardening. Just now we discussed that the ultimate stress should be at least 15% higher. So the actual force which the reinforcement bar can take is more than its Fy. So to take that increase into account, a factor of 1.25 is used. So this 1.25 T1 plus T2 minus the shear force in the column, that will give you the joint shear. In case of exterior column, we can see that there is only force acting in this direction. Okay, and this is VC. So it is T1 minus VC. T2 is not there. The left side beam is not there. That's why there this expression changes to, sorry, I have made a mistake while writing this expression. Actually, this is not there. It will be 1.25 Fy AST1. You can check in the code. It is 1.25 AST1. There is no AST2 because there is no beam on the right hand side. Now this is the demand. It is to be compared with the capacity. How to get the capacity? The capacity depends on square root of FCK. AEJ is the horizontal area of the joint. So if you take a section, horizontal section within the joint, between the beams and columns, so that area is giving you AEJ, and 1.5 times of AEJ if the joint is confined by beams on all the four sides. For example, an interior beam of a building, interior column of a building, which will be having beams on all the four sides. So there it will be 1.5 times AEJ into square root FCK. In case of an exterior column, it will be 1.2 AEJ, which is confined from three sides, but not on the other side. And the corner column, which will be confined, which will be having beams only on two perpendicular directions. Okay, so it will not be confined in any direction. It will be having beams only along two perpendicular directions. There it has to be 1.0. Sorry, I have made another mistake here while making the slide. It is 1.0 AEJ in the code. So depending on the location of the column, we can select the appropriate expression for calculating the capacity. And this capacity should be larger than this demand. The first two expressions will give me the demand. These will give me the capacity. And for any column beam joint, the capacity should be more than the demand. If the demand is exceeding the capacity, then what we have to do? We have to provide shear reinforcement in the joint. Okay. How the shear reinforcement in the joint is provided? In the form of stirrups. Now, in addition to shear reinforcement, in any case, we have to provide confinement within the joint also. So both the codes, IS 1893, sorry, IS 13920 as well as NBC 105 ask for this confinement. No, sorry, I have mistaken. NBC does not write this explicitly. There is a statement given in NBC when I was reading. It is saying that even if it is the joint is not confined, we have to provide the shear reinforcement. Okay, that means that there is a provision of providing the confining reinforcement in the joint, but the clause is not there. Somehow the clause has been missed. But I understand the intention of NBC is also the same. So in case of an exterior joint, the same reinforcement, same special confining reinforcement as maximum spacing 100 will be continued inside the joint. And this reinforcement will act as confinement as well as the shear reinforcement. If the shear reinforcement required for this difference of demand and capacity is more than this reinforcement, then that much will be provided. Otherwise, this reinforcement will take care of the shear reinforcement also. Similarly, in case of an interior joint, this reinforcement is to be provided, but this reinforcement can be reduced. And the code says that this reinforcement can be reduced to half, or the spacing of this reinforcement can be doubled, because here we are having beams on all the sides of the column, and the confinement will come from these beams also, because in beams we are having longitudinal reinforcement. That longitudinal reinforcement will act like a confining reinforcement in the column, and concrete of the beams will also confine the concrete of the joint portion in the column. So here the confinement is there, so from the beams, so we can reduce the spacing. But if it is an exterior joint, if we do not have beam on any one side of this joint, then we have to go for same reinforcement as we have in the column region. Then the next point, next provision in the codes is regarding splicing. So the code says that wherever we are splicing the reinforcement, because we have to extend the length of the bars, so that we can do by splicing. So whenever we are splicing, the spliced portion should be confined with a special confining reinforcement, the same reinforcement which we have provided in the beams. Okay, and the requirement of the spacing are given. So this much reinforcement is to be provided, and not more than 50% of the bars will be spliced at one location, and this splicing location should be in the central half of the members. So only in the middle half of the member we can do splicing, and not more than 50% splicing can be done at one location. Okay, and area of the transverse reinforcement, this is given in NBC 105. Using this expression, you can calculate the size of the hoop bar, the bar which is making hoop. That size you can obtain using this. Okay, same expressions are given, same provisions are given in Indian code also, except that this expression, the method to calculate the transverse reinforcement is not given, and generally people are using the same reinforcement which is required for special confinement in the beam. Same reinforcement they are providing. Okay, but the Nepalese code has come out with this expression, which is different than the transverse reinforcement required in confinement zone of a beam. Hopefully, I mean, I do not know, but most probably this will come out to be lower than that. So requirement will be less than what we are having in the potential plastic hinge region. Okay, so that's about the confinement of concrete and anchorage of the reinforcement. Then, even if we do all this confinement and anchorage, we can make our RCC members ductile only in bending. So in bending, those members will be ductile, but those will still be brittle in compression. So under compression also it will be brittle failure, and under shear also our members will fail in a brittle mode. In comparison to steel, if you see, in comparison to concrete, if you look at steel, steel is ductile in bending, steel is ductile in axial action, steel is ductile in shear. Steel is brittle, only steel members are brittle only in compression, because under compression those are prone to buckling. But concrete is RCC members, even after proper confinement, adequate stirrups, we cannot make it ductile in shear mode. Okay, so if only one mode is ductile, will our structure be really ductile? That is the question. And to ensure that, we use capacity design. So this capacity design concept can be understood with an example of a chain which is having several links. Out of these links, all the links are brittle except one. So only one link in the center, this black one, this is ductile. All other links are brittle. And this link is subjected to large force, so that this chain is going to fail. It is similar to earthquake, because earthquake is also much larger than the capacity of the structure, so the structure has to fail. So same way this chain has to fail. Question is, when I have only one link as ductile link, will it fail in a brittle mode or in a ductile mode? Only one link is ductile, all other links are brittle, and I am applying increasing force. The force is going to increase the capacity and the chain is going to fail. So whether the failure will be brittle or ductile. It is similar to our frame, where our members can fail in ductile manner only in flexion, not in axial force, not in combination of axial force and bending, not in shear. So this chain will fail in a ductile manner if the ductile link is failing first. But if the brittle link is failing first, then it will fail in a brittle manner. So whether the chain will fail in a ductile manner or brittle manner will depend on the hierarchy of strength of different links. If the brittle links are having higher strength than the ductile links, it will fail in a ductile manner, because in that case the weaker link, which is the ductile link, that is going to fail. So the key principle is that if I want to make my structure behave in a ductile manner, what I have to ensure? I have to ensure that the brittle links, the brittle modes of failure should be stronger than the ductile modes of failure. Then only the ductile mode will be the weaker link, and that is going to fail. Otherwise, a brittle mode will become a weaker link, and that will fail. So I have to ensure that the brittle mode should not be the weaker link. That should be the stronger link. Its strength should be more than that of the ductile mode. I'm not saying that the strength of the brittle mode should be more than that of earthquake. Earthquake is in any case much stronger. But what we can ensure is that the brittle link or the brittle mode of failure is stronger than the ductile mode of failure. One such issue is that when we are doing the capacity design, we should know that where the failure is going to occur. That means all the potential plastic hinge regions should be clearly known. Then only I can do that. Because if I do not know where the failure will occur and the failure occurs at that location, I can't help it. So I should know, I should have a good understanding of the behavior of my structure, so that I am able to define the potential hinge regions well in advance, so that I can take care of those. Then undesirable modes of inelastic deformation like shear, anchorage failure, instability, buckling, those are avoided. How we can avoid those? Making them stronger than the ductile mode, not making them stronger than the earthquake, making them stronger than the ductile mode. And then potential brittle regions are protected by ensuring their capacity exceeds the demand originating from the plastic. In other words, whatever demand on these elements will occur when the when the ductile elements are yielding. So at the time of yielding of ductile elements or ductile modes, how much force will occur in these elements? That force should be used to design of these brittle members. Okay, an example we can take here. This is design of a building. In one case, the columns of a story are yielding, and then it is going to fail in what we call a story sway mechanism or local failure mechanism. In another case, the beams are yielding, and even when all the beams yield, still it is a determinate structure. It is stable, and failure will occur when the columns will fail at the base also. So first, all the beams develop plastic hinges, and then the columns develop hinges at the base, and then it is going to fail. So out of the two, this one is called the local failure mechanism. This is called the global failure mechanism, because here whole of the structure is involved in failure. You can see I have shown the cross and the right tick mark here. That shows that the global failure mechanism is preferable. Why the global failure mechanism is preferable? Because here we are having a larger number of plastic hinges, so we get more energy dissipation. That is one thing. Secondly, the hinges are forming in beams, and in beams, the beams are subjected to flexion, not to the axial force. Axial force is registered by the slab. So beams are not subjected to axial force. Beams are subjected to almost zero axial force or very little axial force. And as a result, the ductility of beams is much more than the columns, which are subjected to axial force, PM interaction. So there the ductility is much less. That's why this is a preferable mode. And how we can ensure that the beams yield before columns? We have to make columns stronger than the beams. So a strong column, weak beam design is the key philosophy of capacity design. We have to make the columns stronger than the beams. Means at any joint, if I take the sum of strength of all the columns and sum of strength of all the beams, the strength of columns should be more than the strength of the beams. And here we are talking about strength, not the applied moment. Strength. Strength will come from the reinforcement you have provided. So after providing the reinforcement for all provisions, you will check. And this ratio of summation MC by MB as per NBC is 1.2. It is from ACI. ACI has this ratio 1.2. IS 13920 has this ratio 1.4. So in this regard, IS 13920 is better. And we have seen from our analysis by performing nonlinear analysis that even when you take summation MC greater than 1.4 MB, you cannot avoid formation of hinges in the columns. Hinges form in the columns in that case also. Under nonlinear time history analysis, the hinges will form. Okay, although we have designed columns stronger. Why? You may say how it is possible. Because once the beams yield, the bending moment diagram in the column changes. And due to that, the hinges form. But those hinges do not form before formation of hinges in the beams. The hinges in columns form later, after the beams have yielded. Okay, and it has been seen that if we take this factor as 1.4, the performance is better than what we are getting in place in case of 1.2. NBC, to avoid practical difficulties, have chosen from ACI this factor as 1.2, but Indian code has this factor of 1.4. So this is one major difference between the two codes. Then, when we are designing a beam or column, we have to ensure that the beam should fail in flexion rather than failing in shear. And for that, this clause is given in the code. Here, when as I said that under earthquake, the beams at both the ends are subjected to the moment in the same direction. So if it is clockwise here, it will be clockwise here. If it is anti-clockwise here, it will also be anti-clockwise. And we can see when this is subjected to clockwise moment at both the ends, there will be a shear force developing here because of this moment. and the shear force will be MUA plus MUB divided by L. So the total moment divided by lever arm between the two reactions. So we will get a reaction 2M by L because of the moment, and we will also have the shear force because of the dead load and live load. So this dead load and live load has been taken 50% because you remember while discussing the seismic mass in the last lecture on last Saturday, we discussed that whole of the live load is not there at the time of earthquake. So we take that reduced live load. So dead load plus reduced live load, and in addition to that, the what is coming because of the moment. And here again, a factor of 1.4 is used. This factor takes into account the over strength due to strain hardening. So actual strength will be maybe more because the steel strength is more than the yield strength. So to take that into account, this factor of 1.4 is there. And because earthquake is having reversal in its direction, so this couple which we are getting at the beam ends, that couple will also reverse its direction. So in one case, the shear due to these moments will be added. In another case, the shear will be subtracted. So we have to consider these four conditions, and we can see that when we are considering this condition, the left end of the beam is in sagging, right end of the beam is in hogging. So it has to be sagging at A, hogging at B, and then hogging at A and sagging at B. Okay, so in one case, sagging at one end, hogging at the other end, and another case, hogging at one end and sagging at the other. Same expression is available in IS 13920 also. Okay, then in case of columns, how to obtain the shear force? We want the columns also not to fail in shear. We want shear mode to be avoided in column also. But we have seen that columns are designed stronger than the beams. So shear force which can develop in the columns will be governed by the beams, not by the column moment capacity. Column moment capacity may be higher, but the maximum shear force which can develop in the column will depend on these moment capacities of the beams. So we take the moment capacity of the beams, add them and multiply by 1.4, divide by the height of the column. Height of the column is same as the height of the story. So that gives the capacity shear in columns. So we have to design our beams and columns not only for the applied shear force, for these capacity shears also. So if I summarize the provisions of the code regarding capacity design, I can summarize in these steps. Just 1 minute. So the steps will be like this. First, we have to design, we will perform analysis using dead load, live load, and earthquake load. Earthquake load will be calculated as we discussed in the last lecture. After performing the analysis, we will get the bending moments, axial force, and shear force in all the members. But we will not design all the members simultaneously. First, we will design the beams. And whatever reinforcement is required for the beams, using different criteria of the code, there are limits due to various regions, minimum reinforcement, shrinkage, etc. So all those requirements we will satisfy, and then we will decide the longitudinal reinforcement, flexural reinforcement in the beam first. Then for this reinforcement provided, we will calculate the capacity, the moment capacity of the beams. This is important. That moment capacity of the beams is to be back calculated based on actually provided reinforcement at top and bottom. Considering it at doubly reinforced section, we will calculate the moment capacity, and for that moment capacity, we will calculate the capacity shear in beams, and then beams will be designed in shear for the maximum of the applied shear and the capacity shear. One shear force we have got from our analysis, another shear force we are getting from the capacity of the beams which we have provided. Whichever is larger, that we will use to design the beams in shear. And then we will design the columns for the applied force and the maximum moment which can be occurring due to beams through analysis or through capacity moment, because we have to keep the ratio of moment capacity of columns to beam to be 1.2. So that moment or the applied moment, whichever is higher, we will use that in design. And then we will design our columns for shear. And when we will be designing columns also for shear, we will consider both the shear, the applied shear and the capacity shear. Capacity shear is coming because of the provided moment capacity in beams. So whatever reinforcement we have provided in the beams, that governs the provided capacity of the beams, and that governs the capacity shear in column. So column will be designed for shear force coming from analysis as well as coming from the capacity design. Then we will provide sufficient anchorage to beams reinforcement, the detailing of the beam reinforcement into the column. We will provide a special confining reinforcement within joint. We have to do that. Then in case of short columns or mezzanine floors, okay. So when we have short column effect, the columns are subjected to very large shear force throughout their height. In that case, the special confining reinforcement is to be provided throughout the height of the column. So when we have short column due to either partial infill or due to mezzanine floor or due to any other region, maybe due to staircase landing, in all those cases, we have to provide the full length of the column as specially confined. So last time somebody was asking about staircase. So one thing we can definitely do in case of a staircase. So when staircase landing is supported on columns at mid height, then whole length of the whole height of the column should be provided with a special confining reinforcement. Otherwise, that column is bound to get damaged during earthquake, severely damaged and column. Damage will be there in any case. And then we provide a special confining reinforcement in foundation for a depth of 300 millimeter. And we should ensure proper arrangement and anchoring of the ties and hoop. 135-degree anchored into the core by 6 times the diameter or 65 millimeter, whichever is higher. Okay, so that's about the beam column frame. Now I want to spend some time on ductile detailing of shear walls also, because in case of taller buildings, we have to go for shear walls as well. You may not be having very tall buildings in the hilly areas, but in Kathmandu and plain areas, there may be buildings larger than 10 stories. And whenever we are having buildings larger than 10 stories, we have to provide shear walls. So how these shear walls are detailed? Now, first question, when we talk about shear wall, the first question asked is that what is the difference between a column and shear wall? At what ratio of width to depth I will treat column as the shear wall? That is one question. Now the answer is no. Column and shear wall are not decided based on the ratio of width to depth. At any width to depth ratio, you cannot call a column, you cannot detail a column as a shear wall. Then how to decide the column and shear wall? The decision of column and shear wall is done based on the bending moment diagram. So here what you see is the bending moment diagram in beams and columns of a frame. So left side is showing the distribution in columns and right side is showing the bending moment in beams. So what you see here is that there is point of counterflexure near the mid height in columns. So the bending moment diagram in columns will be such that there will be a point of counterflexure in the middle. On the other hand, if you see the bending moment diagram in shear wall, you can see near the floors, there is a jump in the bending moment in the shear wall also, but there is no point of counterflexure. It is cutting the zero line only at one point here. Okay, so there is a sawtooth type of variation because the beams can cause, which are connected to the shear wall, or if it is a coupled shear wall, then the coupling beams can cause change in the bending moment diagram in the shear wall, but it will not cause reversal of the direction. Like here, what is happening in each story, the bending moment is changing the direction, positive to negative in all the columns in every story. So that is the difference between a shear wall and a column. And you can see, if you are designing a column, then column needs to be provided with a special confining reinforcement at each story, at top and bottom, because there is a possibility of plastic hinge here and here. But if you see the shear wall, where the plastic hinge will occur, the plastic hinge will occur where the moment demand is maximum. That means at the base. So here the possibility of formation of plastic hinge is at the base or near the base. Okay. So we have to do special ductile detailing in this portion. So how the ductile detailing will be done, whether it will be as per shear wall or it will be as per column, will be decided by the bending moment diagram. Okay. And in shear wall, we want that the plastic hinge should form at the base, not at the height. So what we have to do, we have to enhance the bending moment diagram. Now this capacity moment, which is used in design of shear wall, is neither available in Indian code nor available in Nepalese code. It is there in ACI and Euro code. And what is done here, that first this is the original, the sawtooth type bending moment diagram is the original diagram. Then what we do, this portion of the bending moment diagram, which is in the opposite direction, we reverse it because earthquake is causing reversal. So this much bending moment will be acting on both the sides. So we consider the bending moment in both the sides, and then we join the top and bottom bending moment by a straight line. So this becomes an envelope. And then this envelope we amplify. How do we amplify? That for a height, which we call critical height, this is representing the height which is going to yield. Generally, it is equal to 1 story. So for that 1 story, we will keep the bending moment demand same. And after that, we will draw a line which will be parallel to this envelope line, which we have obtained by joining, which we have drawn as an envelope of the actual bending moment diagram. So this envelope I enhance in such a way that it is constant up to HCR, and then at any other place there is a sufficient margin. Okay, so that when the plastic hinge forms here, there is no hinge forming in the upper portion. There is sufficient margin for the bending moment in the upper portion. Because if the shear wall develops a hinge somewhere in the middle, then its ductility is going to reduce. So to avoid that formation of the plastic hinge at the middle, somewhere middle, not at the bottom, we have to go for this type of enhancement in the bending moment diagram. This is the capacity design concept for bending moment in shear wall. It is not included in both the codes, neither in NVC 105 nor in IS 13920. So please, when you are using shear walls, use this. It is available. More details are available in ACI 318 if you are interested. Then there are different types of shear walls. We can have squat or low rise shear walls. Squat shear walls are those where the height is less than the length. Actually, this dimension, horizontal dimension of the shear wall, we call length, not the width, not the depth. We call it length. So this is the length, this is the height, and perpendicular to the plane of my screen, that is the thickness. Okay, so height to length ratio, if it is less than 1, we call it squat shear wall. And if height to length ratio is more than 2, we call it slender wall. So there is a squat shear wall, there is a slender shear wall. And you can guess the squat shear wall is going to fail in shear mode. It cannot fail in flexure. On the other hand, the slender shear wall, if the height to length ratio is more than 2, the failure will be in flexure. So shear failure is going to be brittle. The slender wall, which is failing in flexure, bending, that is going to cause good ductility. So we will get good ductility in case of a slender shear wall. Then we can have a shear wall with openings. These openings can be arranged in number of ways. This is one way. Another way of arranging the openings is this, where the openings are arranged vertically along the center of the shear wall. Now here, what happens? This shear wall gets divided into two walls. One wall is here on the left of the opening, another wall is on the right of the opening, and in between it is connected by deep beams, what we call coupling beams or spandrel beams. So it gets connected by these spandrel beams, deep beams. So it acts like two walls coupled together through these coupling beams. That's why we also call these walls as coupled walls or coupled shear walls. These coupled shear walls have some advantages of frame and some advantages of shear wall, both. That's why this is a very efficient system. And here these I will show later, these coupling beams, these are subjected to large stresses, these are subjected to damage, these dissipate the energy, and then there is a possibility that I can design these coupling beams in such a way that these can be replaced. Once these get damaged during earthquake, these can be replaced. So the building can be repaired easily. Then the shear walls can be provided in all shapes possible. You can provide a shear wall core, you can provide a planar shear wall. Before starting today's lecture, somebody was asking that if we have a shear wall core, shall we call it dual building or not, dual system or not? Yes, if you are providing shear wall in the form of a core, you may provide shear wall in the form of a T, L, C, I, any section. Or sometimes there is a shear wall where the end boundary elements, the size of the boundary elements is increased. So this is also shear wall. These all are examples of shear wall, and you can provide shear wall in any shape depending on the functional requirement in your building. The only problem with shear wall, providing shear wall, is that it is a permanent partition. It will block the ventilation fully. Okay, that's the problem. But wherever you have that facility available, you can afford from the functional design point of view, you can use shear walls because it is a very efficient system. It increases the strength as well as the stiffness of the building significantly. Now in a building, where should we locate our shear walls? So the shear wall should be located in such a way that these are placed symmetrically. It should be symmetric so that the center of mass and center of stiffness are coinciding. There is no torsional irregularity. Secondly, these should be provided as close to the perimeter as possible. The reason is that when these are provided close to the perimeter, the torsional rigidity is more. Okay, and under accidental torsion or even some real torsion, the delta max by delta min will be reduced when the torsional rigidity will increase. I can show you with this plan. So suppose this is a building. Here, this A, B, C, D, E, these are the shear walls provided. So you can see that these shear walls are provided in such a way that A is balancing B, so that the center of stiffness is here near the center of mass. Then C and D together are balancing E, so that the center of C, D, and E is here at the center, so that there is no eccentricity, there is no torsion. And when it will be subjected to a force, let us say in vertical direction, then these two walls, A and B, these will be resisting the force, and the resultant should be here. When the force is applied in this direction, then C, D, and E will be resisting, and the resultant of these forces should be equal and opposite. It should be acting at the same point where this earthquake force is acting. So that's how the shear walls are to be balanced. Now, let us say we are giving a moment here. I apply a torsion at the center. Then what will happen? All the shear walls will resist the force. When it will try to rotate, the floor slab will try to rotate. The shear walls will oppose that, and those will have forces in the same direction. Okay, such that it is opposing that movement which the rotation, that torsion is trying to do. And the torsional resistance will be equal to force into lever arm. So for each force, whatever lever arm it is having from the center of stiffness. So larger the lever arm, more torsional resistance you will get. Okay, so that's why I told that these shear walls should be provided as far away from the center as possible, so that the torsional resistance is maximized. Now, this is the ideal situation. You can't do it in all the buildings. It will be governed by the functional design. So depending on the functional design, you decide, but your choice, your effort should be to provide these shear walls in such a way that you get the maximum torsional rigidity, and at the same time, the shear wall should be torsionally balanced so that there is no accidental eccentricity. Then in shear wall, in any shear wall, two portions are important. One is what we call pier and another what we call a spandrel. A spandrel is nothing but a beam. So a horizontally spanning system or component we call a spandrel. So in the first figure, what you see, these are the spandrels. These will be designed as beams. So here the bending will be about a horizontal axis. Okay. Then these vertical portions, these will be acting like cantilevers or vertical bending elements. So these will be designed like columns. The spandrels will be designed like beams. The piers will be designed like columns. So these shaded portions, these are the piers. So we have to identify in any shear wall that which is the pier portion and which is the spandrel portion. And accordingly, their reinforcement is to be calculated and it is to be provided. It is to be arranged. For example, in a column, we will like that more reinforcement should be provided at the edges, vertical edges. So near the openings, there should be more reinforcement. Similarly, in case of a spandrel, more reinforcement should be at bottom and at top, because the reinforcement, the bending moment due to earthquake will be reversed. So the placement of the reinforcement will depend on the function of that portion of the shear wall. So we have to understand the function of these portions of the shear walls correctly. Now, some common failure modes in case of shear walls, what have been seen. So here you see the shear wall has failed in shear. So due to in-plane shear, it has failed. The reason is that the shear wall will, due to its stiffness, it has large moment of inertia. So due to its large moment of inertia, it will attract a lot of shear force, and in that shear force, it will fail. And due to that shear force, the concrete got crushed. And you can see that the stirrups have ruptured there. The stirrups failed. And once the stirrups failed, the longitudinal reinforcement buckled and it lost its vertical load carrying capacity. When we say any member has failed, when it loses its vertical load carrying capacity, that is the failure of the member. And here it has occurred because of the crushing of the concrete, and crushing of concrete occurred because of this rupture of these stirrups which were provided. So what lesson we can draw from here? We draw the lesson from here that this portion, at least the end portion of the shear wall, where the concrete can get crushed, it should be confined properly in the same way as we are confining the columns. These portions we call boundary elements, and these need additional confinement, special confining reinforcement. Okay, so this is the boundary element. This figure I have taken from ACI 318. So this portion is called boundary element. So this length, which is length of the boundary element, it should not be less than 2 times the BC. So BC is nothing but the width of the shear wall. So this is BC, you see. So the BC length should be at least 2 times this. So this portion needs to be spatially confined. Okay, and this confinement will be in the same manner as we have in the column. So similar to the column, it should be confined. Okay, the remaining portion also needs to be confined. So this cross ties are to be provided in the back portion also, but the spacing etc. need not to be as stringent as it is here in the boundary element portion. This spacing of the ties and hoops will be governed by the clauses given for column. So same clauses will be applicable here. Okay, different types of arrangements are possible. Now, in case of, this was in case of planar wall. In case of flange walls, what portion should be confined? That will depend upon the direction of the moment. So for example, if the direction of the moment is in this direction by this double arrow, so double arrow gives actually the direction of the moment using right hand thumb rule. So if you take your thumb in the direction of the double arrow, the fingers will give the direction of the moment. So what you see here, this direction of the moment, it is causing compression in the shaded portion. So this shaded portion, which will be in compression, that needs to be confined. For the reverse direction, this needs to be confined. So in other words, whole of this will be required confinement. Now, if this is the direction of the moment, then this portion will be requiring confinement. Okay. And similarly here, if the moment is about this axis, then we can see that the compression will occur in this portion and this will not confine. So in this case, whole of the shear wall, you can see, because the bending moment can come in any direction due to earthquake, and it will be a combination. So it can be about an inclined axis as well. So whole of the portion will be subjected to the compression due to some action of earthquake, and that's why the whole section needs to be confined. In case of a planar shear wall, you can confine only the boundary elements, in between you can leave, but here there is no portion which you can leave. So whole portion needs to be confined. Okay. Then in case of flange shear wall, the flange provides additional capacity to the bending of the wave action. So appropriate flange width. Expressions for this flange width are available in both the codes. So maximum width can be equal to 1/10 of the height. So whatever is the height of the shear wall, 1/10 of that can be considered as the BE. And we can see that this BE will be very small at the top, equal to the thickness of the web. And as we go down, due to dispersion, this will go on involving larger width. And the maximum it can involve is 1/10 of the height, or the actually physically available width, because it cannot go outside the shear wall. So within the shear wall, whatever is the maximum available, or 1/10, that much we can use maximum. Okay. So there are some requirement in NVC. Minimum thickness greater than 150. Actually, it is same as IS 13920. And for coupled shear walls, it has to be 300 millimeter. In coupled shear wall, we will see later that we need special reinforcement. We have to place the reinforcement properly, and that's why the larger thickness is needed. And length to thickness ratio has to be more than 4. Minimum reinforcement is 0.25%, and the shear stress has to be less than 0.25 FCK. So this is tau C max. So shear stress should not be more than tau C max, because more than that, the concrete will get crushed in the diagonal compression action. So whatever reinforcement you provide, you cannot resist shear stress more than tau C max. And the longitudinal bar dia should be less than, we should not use very large diameter in the longitudinal bars. It should be less than 1/10 of the wall thickness, and the spacing should be smaller of these three, not more than 450, not more than 3 times the wall wave thickness, and not more than 1/5 of the length of the wall. Okay, so at least 5 bars along the length should be there. Okay, and 3 times the thickness, there should be 1 reinforcement bar, and not more than 450 millimeter. And if tau B is greater than tau C max, you have to redesign. If tau B is between tau C and tau C max, you have to provide reinforcement. And if it is less than tau C, then you have to provide minimum shear reinforcement. And shear reinforcement in shear wall is provided in the horizontal direction. So a shear wall, a typical rectangular shear wall, will have vertical reinforcement as well as horizontal reinforcement. Horizontal reinforcement will resist shear, but shear crack is at 45 degree. So shear is resisted not only by horizontal reinforcement, by vertical reinforcement also. So vertical reinforcement will be governed by shear as well as flexure, whichever is requiring higher reinforcement. Horizontal reinforcement will be governed by shear force only. And this concrete shear stress tau C, you can get either from IS 456 or using this expression. So using this expression, you can calculate what is the permissible tau c, and if shear stress, average shear stress in my shear wall BAB is less than this tau c, then I will provide the minimum reinforcement of 0.25%. This is the minimum reinforcement. So this in horizontal as well as in vertical direction, the reinforcement cannot be less than 0.25%. Okay. Otherwise, I will calculate the horizontal as well as vertical reinforcement based on the difference between VU and tau CTV. So using this expression, I can calculate the horizontal reinforcement. And if this is more than the minimum reinforcement, this will be provided. Okay. Similar expressions are there in IS 13920 also. Only thing is that only difference is that in IS 13920, the clauses for minimum reinforcement are slightly more elaborate. So minimum reinforcement, horizontal reinforcement is same, 0.25% as it was given here. But the vertical reinforcement, minimum vertical reinforcement is slightly higher than 0.025, where this factor also comes. It depends upon the height to thickness ratio. So depending on height to thickness ratio, this will improve. Okay. Then we have the boundary elements. So rho V in the boundary elements, this is 0.8%. It is there in NBC also. So 0.8% is the limit which was given in IS 456 for columns. Now NBC has changed this limit to 1% in the column, but it has continued with 0.8% in case of the boundary elements of the shear wall. So boundary elements of the shear wall, these are the portions along the edges of the shear wall where the maximum compressive stresses in concrete will occur. And if the compressive stress exceeds a given value, then that needs to be confined. In NVC, that part is not given, that at what stress level it will be required. It looks like that NVC is recommending this in all the cases. The boundary element will be provided throughout in all buildings, all shear walls, irrespective of how much bending moment and axial force is acting. The boundary elements needs to be provided, and this boundary element will be 2 times the wall thickness or 0.2 times the wall length, 20% of wall length or 2 times of the wall thickness. In that portion, the special confining reinforcement will be provided, and longitudinal reinforcement will also be concentrated there. The minimum longitudinal reinforcement is 0.8%, and it should not be more than 6% and should be 4%, the same limits as we had for columns. Okay. A special confining reinforcement will be same as that for columns. So using the same rules, we will calculate the special confining reinforcement. This is how a properly detailed reinforcement in a shear wall will look like. You see how it is looking like. So these are the boundary elements of the shear wall. In between, this is the BAB reinforcement. So this type of reinforcement is to be provided. Here you can see the cross section. This portion is BAB. In BAB, you can provide lower reinforcement, but in the boundary elements, you have to provide larger reinforcement. If you are concentrating more reinforcement in the boundary elements, then the moment capacity will also increase because the lever arm is going to increase. At the same time, this will provide better confinement. If you are having more number of bars, longitudinal bars, which are restrained against lateral movement, outward movement, you will get better confinement. Okay, then the axial force, which can be computed for design of these boundary element, the NBC gives this formula. It is a simplified formula which was there in the earlier version of IS code. Now in the recent version, when it was revised into 2016, this formula was dropped, and what IS code demands is that we should consider the full section of the shear wall, and that full section, like this one, all the reinforcement we should consider, and we should design this full section for the combined action of P and M. So what we have to do, we have to develop PM interaction similar to columns for this whole section, and then that PM interaction curve should be such that all the applied pairs of P and M should be within that. Okay. So taking into account the actual distribution, we can model it in any software, section designer or any software, and we can plot the PM interaction curve, and then we can use that for design. This is a simplified formula where you can calculate the axial force in in boundary elements, and then you can design the boundary elements as short columns. So it is a simplified method, approximate method. Okay. So in case of IS 13920, the extent of the boundary element is also defined in terms of stresses. This clause is not there in NBC, and wherever the combined stress due to P and M based on gross section exceeds 0.2 times FCK, the boundary element is to be provided. And where it is less than 0.15 FCK, you need not to provide. You can discontinue the boundary elements. But NBC does not allow to discontinue. Please keep in mind, NBC has not given any such clause. So that means you have to provide boundary elements in all the shear walls throughout the height. Okay. Then the special confining reinforcement, this expression is given. Similar in both the codes. Then we have to provide, as I have shown in the beginning also, the shear walls have to be provided with openings, and near the openings, the shear walls are having concentration of stresses, and these are prone to damage. So what to do near the openings? So in case of spandrels and shear walls, piers, we have to take care. Okay, and there are some clauses given in code regarding the piers. So when we have shear wall with openings, then we should ensure that the structure is integral in terms of flexural strength. That means due to opening, the size and location of the opening should be such that the flexural capacity is not affected tremendously. Okay, because what will happen if I am having opening in the boundary element close to the boundary, then I can see that the flexural strength will be reduced significantly. And I should ensure that that flexural capacity is enough to resist the forces which are expected to come on that building. So otherwise, the opening should be located near the center of the shear wall, so that its effect on bending moment is not significant. Then the shear strength will also be reduced because the cross-sectional area is going to reduce. So the shear strength has to be calculated by considering the reduced area. So remove the dimension of the opening from the total length of the shear wall and calculate the shear stress there. Then irregularly placed openings should be avoided. So if the openings are irregularly placed, then the piers and spandrels will not be clearly identified. And in such cases, where the piers and spandrels cannot be clearly identified, we should avoid. Ductile detailing will be difficult. And then substantial energy dissipation takes place in coupling beams in case of coupled shear walls. And these are weaker than the main walls. These should be weaker. It is desirable that these should be weaker than the shear walls. So for example, if I have, these are the different types of coupled shear walls you can see. So here two shear walls are coupled, which are equal. Here two shear walls which are unequal are coupled. Here several shear walls are coupled. And here the shear walls are having longer, taller openings. Okay. In all these cases, you can see that the beams are weaker than the shear wall. That is desirable. That the damage should occur in the beams, not in the piers. It should occur in the spandrels, in the beams. So beams should be weaker. On the other hand, if you have this type of system where the spandrels are quite strong, but the piers are weaker, so what will happen? The failure will occur in these spandrels. Spandrels are like columns, and this failure will occur in shear. So we have to avoid this, because when these spandrels fail in shear, it will lose its vertical load carrying capacity and collapse will occur. On the other hand, even if these spandrels fail in shear, the vertical load carrying capacity of the structure is not lost. The structure will continue to resist the vertical load. The collapse will be avoided. That's why this system is desirable. This system is undesirable. Okay. Now, similar provisions are there in IS 13920 also. And it says that in case of openings, we have to provide additional steel along the edges of the openings. And this additional steel which we are providing along the openings should be at least equal to the area of the steel which has been interrupted because of the opening. Because when we are providing the opening, some of the steel has to be cut short. It has to be interrupted. It cannot continue. So that much steel which we have discontinued, that much steel should be provided. Then the vertical bars along full height where opening is present, full story height we should provide, and horizontal bars along the openings in the length of the tension, what we call development length in tension, LD. So LD should be continued horizontally beyond the opening, and in the vertical direction it should be continued at least up to LD, and also for the full story height. It should not be curtailed within a story. Now, in case of coupled shear walls, when the shear wall is deforming, we get a very peculiar situation. So this shear wall is deforming like this. Now, a plane section, if I take in the shear wall, plane and perpendicular to neutral axis, it will remain plane and perpendicular to the neutral axis after bending also. So this section will bend here. This section is going to bend like this. And in between this beam, this will be subjected to very large bending and shear stresses. And this beam, this coupling beam, this beam is going to damage. You can see these coupling beams will be subjected to very large shear force and bending moment, and these are going to buckle. Oh, sorry, these are going to get damaged. These can damage to such an extent that the concrete inside this will get crushed. So you remember in our normal reinforcement detailing for shear force, what we are doing? We are having longitudinal reinforcement, we are having vertical reinforcement. And this arrangement is resisting vertical shear force. Now, you may think how this arrangement can resist vertical shear force, because it can deform like this. Why it does not deform like this? Because there is concrete here. Concrete acts like a strut. So concrete completes the truss, and that's how it is able to transfer the load. If tau c is greater than, or sorry, tau v is greater than tau c max, what is happening? This strut, concrete strut, get crushed. This fails. So this truss action of our normal reinforcement detailing in shear is not working. In that case, we have to use the diagonal reinforcement. So wherever the stresses in coupling beams exceed this value, we have to go for diagonal reinforcement. This is the diagonal reinforcement. So this diagonal reinforcement is to be provided in such a way that this diagonal reinforcement can take full shear force. So whatever shear force is being applied, that can be taken care of by the reinforcement provided along these diagonals. So these diagonals are nothing but bundles of bars, minimum 4 bars, and this is having confinement around this, like it is shown here, and this is inside the main reinforcement. So this main reinforcement, which is provided in horizontal and vertical directions, it is inside that, and it is crossing, it is crisscrossing. So this reinforcement, diagonal reinforcement, is to be provided in such a way that the reinforcement is crossing and it is inside the main reinforcement of the shear wall. That's why you remember the minimum thickness in case of coupled shear wall was 300 millimeter, so that this reinforcement can be adequately accommodated. Otherwise, if the thickness is small, this bundle of bars cannot be accommodated there. Same figure is given in Indian code also, same expression is there in IS 13920 as well. And this vertical reinforcement you see here, this is actually the boundary element, because both these shear walls will have the boundary elements along these edges. So the reinforcement detailing will be done like this, these boundary elements, and then here we will be having these bundles of cross reinforcement. And this bundle of cross reinforcement has to continue, has to be anchored into the shear wall concrete for a length of 1.5 times LD, not LD, 1.5 times LD. Both the codes talk about that. So anchorage length at connections with walls is 1.5 times LD. This is there in NBC as well as in IS 13920. Both the codes say that. Okay. Lastly, coming to the capacity design, which we have discussed earlier, this is the bending moment envelope. We draw a straight line envelope, then we enhance this table. This is not available in our codes. So for this, we have to either use EC8 or ACI 318. Okay. So in case of shear force, the envelope is decided like this. This is the original shear force diagram. Okay. Then we enhance this by a factor given in ACI 318. We continue this up to 1/3h, and above 1/3h, we design it for this constant shear force. So this is the capacity design shear force envelope for shear wall. How the shear force in the shear wall will be used in design. Unfortunately, both our codes are missing this point at the moment. So you can refer to the Euro code or American code for this purpose. Then any member we are constructing, we have to provide construction joint. We cannot construct whole building in one go. So shear wall is also having construction joints, and there is a possibility of sliding shear failure at the construction joint. So to avoid that, the reinforcement across the construction joint should be adequate. And which reinforcement is preventing the sliding of the shear wall at the construction joint? This is the vertical reinforcement, which we have calculated just now. So that vertical reinforcement should be adequate as per this formula to resist this horizontal sliding. And this splicing of and confining in case of boundary elements has to be following the same rules as are there for the columns. Both NBC as well as IS 13920 state that. Okay. So thank you. That's all I wanted to discuss about ductile detailing of frame and shear walls. Whatever questions you have, we can take up those now.
Thank you very much, sir. That was an interesting session on ductile detailing, capacity design, and shear wall design. So there are some questions available in chat box section, sir. Shall we start with that, or shall we directly interact with our participants, sir? What do you say?
Take up questions first, which are given in the chat box. So perhaps you can read the question and I will answer.
Okay, sure, sir.
So
Sure.
I can unshare my screen now. Okay. So you read the question and I will answer, please.
Okay, sure, sir. So our Sudeep sir have asked a question: do structural members goes on cracking state during serviceability limit state, as we use stiffness modifier in serviceability limit state?
Okay. See, in case of earthquake, serviceability limit state does not have much sense, because earthquake is an extreme phenomena, and its design is governed by ultimate limit state. Okay. So these code, actually this problem started when this IS 16700 was published. If you look at IS 1893 and IS 13920, it doesn't talk about serviceability limit state. There is no serviceability limit state for earthquake load. Serviceability limits are there for dead load, live load, temperature, etc., which are permanent loads. For earthquake, serviceability is not there. In IS 16700, they talked about serviceability limit state. And you are right, at the serviceability limit state, we are not having the same level of forces. Okay. So different modifiers should be used. There will be some cracking, but that cracking will not be that severe as we are having in the ultimate state. So different modifiers should be used. And in IS 16700, if you look at, there are two sets of modifiers given, one for wind load and serviceability earthquake load, and another one for ultimate earthquake. That we should.
Okay, so we have a question from DRP user. Can we use different grade of concrete from cost perspective, like M30 for beam, column and footing, whereas M20 for slab and staircase?
We can use, actually in India it is quite common that people are using a lower grade for beams and slab, because in beams higher grade of concrete does not provide any advantage in moment capacity. So if you see the moment capacity is governed by the reinforcement and the depth. There is only little, very little marginal effect of the compression reinforcement and the concrete. So in beams and slabs, we do not get advantage. So that's why people tend to use a lower grade for beams and slabs and a higher grade for columns. But you have to be careful about beam column joint, because beam column joint is part of beam as well as part of column. And if you are using a lower grade concrete in the beam column joint, then there will be problem. So the joint should be cast along with the column. That care we have to take. But otherwise, you can use a lower grade for beams and slabs.
Okay, Utkarsh Vetwal have asked, should we consider the contribution of concrete shear strength tau c in designing for shear for beam according to NBC?
Okay, so it is not that the concrete is not contributing. So when this proposal came in IS 13920, that when we are calculating the shear strength, actually it has come from ACI 318, and there the explanation is also given. So it is not that the contribution of shear is not there, but what happens during earthquake, the member is subjected to, any beam is subjected to, or column for that matter, is subjected to cyclic loading. And due to that cyclic loading, there is successive cracking and sliding. And due to that, the shear strength reduces. How much reduction will occur? That is difficult to estimate. So what code has said, that if you ignore the contribution of concrete and consider the contribution of steel in full, that will take care of the cyclic nature of the load. Actually, it will be contributed by both, and then it will be reduced because of the cyclic nature. So what people have found in research, that if you ignore the contribution of concrete, you estimate the lower shear strength based on contribution of steel alone, that will be close to what we are going to get in case of a cyclic loading condition. That's why the recent codes have provided not to consider the contribution of concrete. That is there in ACI 318 as well as IS 139 also.
Okay, Sudeep have asked a question. In the region of yield movement, expected movement will be maximum, means shear force will be low in that region. Purpose of providing more closer stirrups in that region is just for ductility.
No. Shear will not be minimum. Let me share my screen. Then I will explain to you. Yeah, here I can share my screen. Okay, so if I have a beam and this beam is subjected to bending moment at both the ends, let us say MA and MB. So to counterbalance this, we will have the couple here, and VA and VB, and VA and VB will be equal to MA plus MB divided by L. Okay, so shear force diagram will be actually like this. So this is the shear force diagram due to the earthquake, and we can see that shear force is maximum at the support, not minimum. So at the support we are getting maximum shear force, and at the support our concrete will get crushed because the bending moment is also maximum here. Sorry, just a minute. I have done wrong. Shear force diagram will be like that. And the bending moment diagram will be, I'm plotting it on tension side. So here tension will be at top and here tension will be at bottom. So this is BMD. And this is SMD. So shear force due to earthquake is uniform throughout the length. Okay. Now, due to dead load and live load, the shear force is changing. It is linearly varying. The shear force due to dead load and live load is maximum near the joint. So the total shear force, which is occurred due to earthquake and dead load and live load, will be maximum at the support near the joint. That will be maximum. And bending moment will be maximum because the earthquake bending moment is maximum near the joint. So bending moment will also be maximum. Shear force will also be maximum near the joint. That's why the yielding will occur there, and we have to provide confining reinforcement to take care of the yielding, and we have to provide shear reinforcement also more near the support because there the shear force is going to be higher. Okay.
Taken Pandit have asked, with the increase in axial force, the ductility of the column will be less, and from PM interaction curve, with the increase of sectional dimensional axial force will be more, so that for ductility purpose, it is advisable to use slender column rather than squat column, especially in bridge pier where axial force is very high. Shall I repeat the question, sir, or is it okay?
I could not get the second statement. What you were saying?
PM
Why
interaction.
the shear will be large?
With the increase in axial force, the ductility of the column will be less, and from PM interaction curve, with the increase of sectional dimension, axial force will be more, so that for ductility
Why axial
purpose,
force will be more? This I could not get. That if you are increasing the dimension, why axial force will be more? So let me explain this. Again, I will share my screen. All right. So PM interaction curve of a column is like this. Okay. This is P equal to 0. Means here the column is acting like a beam. Here it is tension, here it is compression, and somewhere here it is the balance failure. So below this, the failure is governed by tension. So tension controlled failure. That means the steel is going to fail first. Above this, it is compression control. So in case of columns, we do not have under reinforced and over reinforced columns. Why? Because the reinforcement in any case is provided uniformly on the four faces. So we cannot have under reinforced or over reinforced. In case of a column, the under reinforced or over reinforced behavior is governed by the axial force. So if the axial force is below the balance failure, then it will act like an under reinforced column, tension control, where the steel yielding will govern the failure mode. Okay, so it is required that all the columns should be designed in this range. We should not design our columns in this range. That's why the columns put a limit on the value of PU. Okay, so this PU should be less than 0.4 AG FC dash. So axial force in the column should not be more than this. How we can reduce the axial force in the column? By increasing AG. Axial force will be coming from the loading. Loading I cannot change, but I can change AG. So area of the column should be selected in such a way, the cross section should be suggested in such a way that the column is in axial control range. In no case the axial force should be more than 0.4 AgFC. Okay, and this will enhance ductility. So it is not the slenderness which is going to cover. governed. Okay, it is the axial force which will decide. Axial force should be much less than the axial capacity of the column. Okay, I hope this question is clear. If it is not clear, please do ask again, whatever is remaining. Okay, for the
Yes.
time being, we will move to the next question.
Biswaballa sir have asked a question. He's trying to suggest something. I think the course will provide some sort of
Oh, sorry,
guidance.
just a minute, hold on. I have not shared my screen. I was drawing something and I have not shared something. So that's what I was. Are you able to see my screen? This PM interaction curve I was drawing, were you
Yes,
able
sir.
to
Yes,
see?
sir. Yes, sir. We can see this.
Okay, okay, then it's fine. Okay.
Biswa sir is trying to suggest something. I think the course will provide some sort of guidance for the reinforcement congestion, especially in beam column joints at the corner. There is no point having proper reinforcement, but concreting is not proper.
No, no, what was the suggestion?
I think the course should provide some sort of guidance for the reinforcement congestion, especially in beam column joints at the corners. There is no point having proper reinforcement, but concreting is not proper.
No, no, concrete can be done proper. We have to learn how to do concrete properly, even providing the reinforcement also. One problem in concreting is because we are using very thin columns. That is normally the problem of congestion. Problem of congestion is not because of the detailing. Detailing is, of course, so detailing is to be done. We cannot compromise with the detailing. If we are compromising with the detailing, then the building is not going to survive the earthquake. So we cannot do any compromise on what is given in the code. What is given in the code is minimum, let me tell you. With this, you can maximum you can achieve is the collapse prevention. So if I take this example to illustrate the point, that suppose somebody comes, some client comes to you for design of his or her building, then what you are going to provide him? You are going to provide that with this code, new code, everything you will do. What you are finally attaining? You are attaining that the building is not going to collapse. That means his financial loss will be complete. Everything will be lost. The building will be damaged. It is to be raised down and constructed again. Some of the family members will die. Only thing you will be ensuring is, if you are following code, that whole of the family will not die because the building will not collapse. Only that much you are ensuring. So there is no room to compromise on that. We cannot compromise. Along with that reinforcement detailing, we have to learn how to do the proper compaction. So for that, first of all, the sizes of our members should be adequate. If we are using very thin columns and then we want to provide the reinforcement, and then of course there will be difficulty. So if we are taking reasonable sizes, then compaction is not a problem. Compaction can be done. Okay, I should not say it is not a problem. It will have difficulty. It has its own difficulty, and construction at site has its own challenges. Designer cannot solve everything. If the person at site is not doing his job, designer cannot take care of everything. That is not possible.
Okay. So Prajwal sir have asked a question. More than 50% lapping means in one grid point or one column to column face.
Whatever total reinforcement in that column is there, out of the total reinforcement, not more than 50% bar should be curtailed. Ideal is that you curtail alternate bars. One bar you splice, another bar you keep continuous, then next bar you splice, and alternate bar you continue. That will be the ideal situation.
Okay, Sudeep have asked a question. How B by C capacity ratio is affected by relative stiffness of slab is because of slab there will be T-beam action which will have higher bending moment capacity than rectangle beam.
Yes. So if you are having monolithic slab, then the beam should be designed as T section. We should take advantage of that in our design also. Usually what happens, we over design our beams and under design the columns. Why we over design? Because we ignore slab, which is actually there. And let me tell you, slab is having advantage not only in compression, it is even more advantageous in tension. We should consider the reinforcement of the slab in tension also. So when it is the beam is subjected to hogging moment, then the reinforcement at the top, we should consider the reinforcement in the effective width of the flange. We should do that. So beams, we should not over design, because when we are designing the beams, then we are over designing the beams, then the columns will require to be over designed further. So beam should be designed only that much as required, that much capacity we should provide, so that you don't have to unnecessarily over design the columns also.
Okay, and the Sudeep have asked another question also. Is it required to model plinth beam, and how reasonable is it to provide lower tie beam in residential building as well? In Nepal, we have a general practice that we do provide a plinth beam, and we also provide a lower tie beam at the foundation level, sir. So he's asking question about that.
It is good. It is good. This practice is good, that we tie the foundations also, so that the foundations move together, and then we provide a beam at plinth level, because that beam will reduce the column height. Okay, otherwise the column height will be more, and it will provide more stability to the structure. So it is a good practice. If you are providing both the beams, it is a good practice. And the plinth beam should be modeled in your analysis. When you are performing the analysis, so whatever plinth beam sizes you are providing, you model that, calculate the forces which are giving, and design it as you are designing any floor beam. In the same way, you design your plinth beam also.
Okay, Taken Pandit have asked a very interesting question. As per code, design of member for shear will be maximum of 1 shear force as per elastic analysis, and 2 shear force due to formation of plastic hinges. My question is, the two criteria will automatically incorporated by commercial software like ETABS or not, and this given value by this software in shear result location should be maximum of these two criteria.
Yes, some of the software like ETABS does that, but there may be some software we may not be doing. So you have to be careful while using the software that it does that, and it follows the latest code.
Okay, Dwarika sir have asked a question. Starting from what minimum structural plan density of shear wall, comma, the time period given by clause 7.6.2 of IS 1893 Part 1 2016 for shear wall building is applicable. If the shear wall plan density is very small, is the formula given by clause 7.6.2 can still be used?
See, there is a amendment in the code. I don't know whether you people have seen that or not. There is an amendment in IS 1893, and where it is given that the period obtained using the shear wall formula cannot be longer than that of the bare frame, and it cannot be shorter than that of the infill frame. So it will be in between. So if the shear wall area is very less and the period is coming out to be longer than that of the frame, then the frame formula will govern.
Okay,
so it cannot be, the period obtained from the shear wall formula cannot be longer than that coming from the frame. So that frame, the shear force coming from the frame formula will be the minimum. That will be governed.
Okay,
and if you have provided infills also in your shear wall building, usually in India and Nepal, there is no building without infills. So that is another mistake our designers do. In fact, the formula for bare frame and that shear wall, the first and second formula of IS 1893 are not valid in our building. Only the third formula is valid, because in all the cases you are providing infills. So the third formula is to be used, neither first nor second. Only in case of some buildings like malls or airport or railway station where you do not have partitions, there you can use those. But in most of the cases, it will be the third formula which will govern the design this year.
Suraj Gurum had asked a question. Sir, if there is torsional irregularity in our building and difficult to balance by shear wall, is it okay to design with torsion as per code or revise the configuration? So this is the problem most of the designers face.
If it is extreme torsion, then you have to revise the section. It is not okay.
So that that greater than 1.2 clause has to be taken care. That extreme torsion means. Okay.
Yeah.
So Man Mehta have asked, we prefer doing concrete We prefer doing cube testing rather than cylindrical specimen. But why then foreign countries still use cylindrical specimen?
So it is not that still they are improved. I mean, they are better. So as I told that the cylinder gives better estimate of the strength as compared to cube, but that needs more expenses. You have to do the capping, you have to do the grinding before testing. So we avoid that, we save the cost. So we are continuing with the old practice of cube. Actually, it should be the cylinder. Cylinder should have been tested. So in developed countries where they have money, they are going for cylinder. We don't have that much money, so we still continue with cube.
Okay, Sudeep have asked a question: how much reasonable it will be to incorporate the stiffness of masonry infill wall in RC frame using equivalent diagonal studs in FEM based software doing the
Okay.
daily design work?
Okay. So here also, I mean, this is very important question. Here also, clarification is there in, I mean, amendment is there in the Indian code. You have to do two designs, two analysis rather. One analysis by considering the stiffness of the infills as struts, and another analysis without these struts. And whichever is giving the maximum bending moment or maximum reinforcement, that you have to use. And invariably, it will be the second case where you are not considering infills. That will give you the maximum bending moment or maximum reinforcement. So what it comes down to? It comes down to that you design the frame without considering infills, but the base shear should be increased as per the empirical formula number 3 given in IS 1893.
Okay. Susan Adhikari have asked a question: building design with using effective stiffness in members making building flexible and hence so time period greater than those model without stiffness modifier, isn't it? So in using equivalent static method, if you use those higher time period, aren't we taking less earthquake forces?
Yes, and that is why the code has said that you cannot design for period longer than what is coming from the empirical formula. See, the effect of period is that as the period increases, the forces reduce, but the displacement increase. Now we have two situations. We have to estimate forces also conservative. We have to estimate displacement also conservatively. If I'm using uncracked section, I'm non-conservative in displacement. If I'm using cracked section, I'm non-conservative in forces. So what code says that you calculate displacement using cracked section, but the forces you scale as per uncracked section, which is the given by the formula given in the code. So both becomes conservative because you are scaling your ground motion. You can calculate the period based on cracked section, but that will be longer and SAYG will be lower. But even for lower SAYG, the SD, if you plot the displacement spectrum, that will give you higher displacement only. So displacement will be larger with cracked section, forces will be larger with uncracked section. So we don't do two analysis, we do one analysis only with cracked section, and the forces we scale using the formula given in the code.
Rohan Shrestha have asked a question: in case of shear walls, why main bars are placed at outer part and distribution bars at inner? In practical field, why analyzing buildings in software through providing adequate size of beam considering deflection criteria, the beam fails in shear and torsion, and even increasing the size of the beam, it fails. So what do you suggest in such issue to pass those beam in shear and torsion?
Sorry, I could not get first
So there are two questions, sir.
Right, right.
So he have asked a question about a shear wall. In case of shear walls, why main bars are placed at outer part and distribution bars at inner?
I don't think so. If I remember correctly, I can look at the code. So we can cross check. I think it is the horizontal reinforcement which is to be provided outside, no? Or it may be vertical bars because of the depth effect, increasing the effective depth. But if I remember, in the code it is given the horizontal reinforcement will be provided outside. Are you sure the vertical reinforcement is to be provided outside?
The vertical reinforcements are provided outside, sir. It's given in the rule.
Okay, then it may be due to the larger depth. Okay, in out of plane, you will get larger bending moment capacity, so it will give you more stability. We do not design shear walls for out of plane moments, but to avoid buckling. Okay, like I have shown in that figure. Now you need more moment capacity in out of plane also. So to enhance the depth, that may be the reason. I'm not very sure, because I was under the impression that it is the horizontal reinforcement which is provided outside to avoid buckling. I will cross check and let you know. Somewhere I read that. I will look in different codes and then I will explain. Okay.
He have asked another question also.
What is the other question?
In practical field, while analyzing buildings in software,
Hmm.
though providing adequate size of beam, considering deflection criteria, the beam fails in shear and torsion, and even increasing the size of beam, it fails. So what do you suggest in such issue to pass the beam in shear and torsion?
Now this happens. This is a vicious circle. This happens in case of short beams. So when you have a short beam, then the shear capacity shear M1 plus M2 by L. So if this L reduces, if L is small, shear force will be more. And there, to increase the shear capacity, you are increasing the depth. So what will happen? The moment capacity will increase further, and then the shear force will increase again. Again, it will fail in shear. You will not be able to pass it by increasing the depth. What you can do is you can pass it by reducing the depth, so that the L by D increases. So L by D has to be large. So you have to design a wider beam in that case. Then it will pass in shear. By increasing depth, if it is a short beam, by increasing depth, you cannot pass it in shear.
So Utkarsh Betwal have asked a question. A plastic hinge in column is allowed to form in base of frame and at top of column in upper story of multi-story buildings.
See, it is not that it is allowed to. It will happen before failure. It will happen. Building cannot collapse before the plastic hinges in the columns take place. And in the top, the plastic hinge will not take place. So it is not that we are allowing. The plastic hinge will not take place. So we are not providing any strong column, weak beam criteria there. That's it. So it doesn't mean that we are allowing the plastic hinge to form there. Okay, because the bending moment in the top column at the top story, top of the building will be very less in the column. And at the base, in any case, it is going to yield. So we have to provide special confining reinforcement and capacity shear design at the base of the column.
Sudeep have asked a question. Park 1986 had suggested to shift location of plastic hinge at least 0.5D or 250 mm, whichever is larger, and 50% of bent up bar from top and bottom bar can be bent up. Why this provision is not included in ductile detailing code of both countries?
So this bent up bar, okay, and shifting of plastic hinge from the face of the column. Actually, in general also, the plastic hinge gets shifted. It does not occur exactly at the face. Okay, it has a finite length. So the center of that plastic hinge is away. So bending the lower bar to the upper face and upper bar to the lower face, that is a cumbersome practice in placement. That's why it is not done. But if somebody can do it, somebody can implement it in field, it can be done.
User DRP have asked a question. When we have short beam span in frame, beam column, can we use diagonal rebars to take shear force when shear demand is greater than concrete capacity?
Yes, wherever the tau is more than tau C max, we should go for diagonal reinforcement.
I think we have reached the limit of the questions, sir. Now all the questions have been taken up and completed.
Okay.
I think now we can interact with our participants. So to make it
Yeah,
more
so if there is
lively,
any other question, I mean, which you have not written and you want to ask, you can ask.
uh, participant can raise a hand or they can unmute themselves also and then ask a question.
I have one question. I think host has missed that question. Sir, is there any reference material or let's say reference thing that can be followed while detailing or let's say preparing drawing details for shear wall? Usually, when I come across we usually have a beam width more than the thickness of shear wall. So, is there anything specific that needs to be followed in such case?
Okay. So connection of beams with shear wall, that is a tricky situation. So that situation happens only in our countries because we are providing shear walls in the same plane of the frame. In developed countries, the shear wall is generally provided in a different frame, generally along the core, and the frames are on the perimeter. So there, this problem does not occur. In our case, the beam may be connected to a shear wall perpendicular to it. The beam may be connected to the shear wall in its plane. Both the situations arise. And when you are connecting a beam to a shear wall, you cannot connect it properly if the thickness of the shear wall is lower than the width of the beam. So in that case, what you have to do, you have to provide a horizontal element in your shear wall along the beam. Okay, so continue the beam through the shear wall. And then this issue of connection will not be there. So provide this beam within the shear wall also. Now let us take the other question, other part where the beam is connected perpendicular to the shear wall. Then there are two possibilities. One is that the beam is connected at the end, at the edge of the shear wall. Then there we are having boundary element. So increase the size of the boundary element to such a way that it acts like a column, and you can connect your beam with that column. Okay. If the beam is connecting to the shear wall perpendicular to it, but in middle of the shear wall, then you have to take a vertical element similar to boundary element. You have to provide an element in the middle which has adequate thickness and reinforcement with which you can connect your beam. Okay. So I hope it is clear.
Thank you, sir. Yes, sir.
Okay, any more questions from our participant sides?
Sir, any reference that can be followed for shear wall detailing with drawings?
There are many books. So the ACI 318, or there is a book by Moहिले. Recently, I have taken most of these photographs which I was showing from Mohile's book. So recently, Moहिले has written a book on RCC design. Okay, so that book you can follow. That gives a lot of details about shear walls.
Sir, is it possible that we can get a personal email or something so that we could get touch?
Yes,
with you?
my email is available on website also. Or I will give here also. But you can always go to the IITR website, go to Earthquake Engineering Department, look at my name, and there the contact email is given. You can always write an email there, but you can also note it down. It is simple. It is yogendra.singh@eq earthquake.iitrroorkee.ac.in. Okay. So if you have any difficulty, any problem, you want any clarification regarding the code, we can discuss. You can write an email. I will try to respond to that email as quickly as possible.
So I will
I have
like
one more question.
Yes.
Sorry. Sir, you have explained that the coupling beams can be like when like we used to design a coupling beams in case of shear wall, so that it will damage. For example, if those coupling beams are damaged, okay, how we can replace it in future, like when it is damaged, or
So
how the detailing can be done?
if it is RCC coupling beam, it cannot be replaced. But if it is a specially designed steel member, even with concrete coupling walls, we can provide a steel member here. Okay, we can provide a steel member here. So this steel member, when it will get damaged during earthquake, okay, this can be replaced. So we can connect it with bolts here. It can be designed like this. Some of the people are following this design. And during earthquake, this portion will get damaged. It will dissipate all the energy. And then after earthquake, it will be removed and replaced by new member.
Okay, so Suraj Gurung asks a simple question. Is it
Yes.
okay to connect slab with lift wall or make it separate at floors?
No, it should be connected, because lift well, you are constructing in shear wall, let us say, then it will provide lot of stiffness and strength to the building. And if you have not connected it with your building, then you are not taking advantage of that shear wall. So it should be connected. The reinforcement of the slab should be anchored into the shear wall of the lift wall, lift well.
Okay.
Okay. Any other question? Or we close?
I guess.
Okay.
Okay, Sudeep
Okay.
Sir, I have one.
asked a question.
Yeah. Yeah, please.
Sudeep, you can ask directly also.
Sir, how can we how can we correct the missing mass correction for the response spectrum analysis if we have a basement
Okay.
in our building?
Okay. Okay. This is very important. So let me first share my screen, then I will explain. You can see my screen, no?
Yes, sir.
So if I have a building which is very rigid in the bottom portion. So what happens when it is vibrating? Only this top portion is vibrating. This portion is vibrating. Bottom portion is moving along with the ground. It is not vibrating with respect to the ground. So when you will do the modal analysis, you will get different modes in this height. The bottom portion you will not be involved in those modes. Its displacement will be more or less zero. And when you will calculate seismic mass, your mass participation will also come out to be very low. This mass will not participate there. So what should you do? First of all, you should consider the number of modes which have 90% of this mass, this W. So 90% of W, which is above that you should consider. And you should calculate the shear force here. That you can do. Now the forces acting on this portion, this will be equal to Z by 2. If we are going by Indian code, then it is Z by 2 into the W of basement. Okay. So what it is, this is our response spectrum, and this rigid portion is having its period here. This is Z by 2. Okay. So we multiply that by this value of a spectral acceleration. So Z by 2 into base weight of the basement into I, importance factor. Okay, divided by R. So SA by G will be taken equal to unity in this case. So that weight you will take, and then for the bottom portion, you will calculate. Suppose you want to calculate shear force here at this location. You want to calculate the forces in your members. Then this will be your VB plus whatever force is acting in the upper portion of the basement above this, that you will add. So the force in basement will be taken equal to Z by 2 into WB into I by R. Okay. So this is the missing mass correction. Missing mass is multiply simply by Z by 2. SA by G equal to 1. Because here this value is unity. Here it is 2 points. Okay.
Sir, is it necessary that if while designing building, we have to cross 60% of our modal mass participation in first and second mode?
I mean, if you are not getting 60% mass participation in first and second mode, it shows that your building is irregular and your modal superposition method is not valid. In that case, you should go for time history analysis. So first of all, you should look why you are not getting 60% mass. Is there any irregularity in your building? Then you should take care of that irregularity. If that irregularity is not allowed by the code, you should correct it. And second thing, you should go for time history analysis in that case.
Sir, I have one question, last question.
Yeah.
So should we do nonlinear analysis for building that is lying on a hilly slope? And what are the precautions we designer must follow for the design of such building?
You mean buildings on hill slopes?
Yes, sir.
Okay.
As
Yes, this is one of the area where we are working currently. This is my favorite area. Earthquake engineering in hilly regions. So when you are constructing the building on the hill, what the code says that you construct building like this. But is it possible to construct building like this on hill? It is not possible. So what we do is we actually provide our columns at different levels. Okay. So first of all, the bearing capacity here, when the failure will occur, it will occur on one side. That wedge failure, we are having a Tarjagi wedge failure. So this wedge failure occurs on one side. It cannot fail to this side. So the bearing capacity is low. On hills is lower. That is the first thing. Second thing, you can see that this building is flexible on this side, rigid on this side. So it will have torsion. That we have to take into account. And third thing is that when it will be subjected to earthquake in this direction, these columns, these will act as short columns. So these short columns need to be avoided. Otherwise, what is happening? These are taking all the load, and whole of the story load will go here, and these will fail in shear. So to avoid that, what you can do is do not provide the beams here. Do not provide the beams here, which can cause this short column. Okay. So the configuration has to be decided in such a way that this short column and torsion is to be avoided. This is the main problem. Otherwise, we have seen that if we follow the codes, we get quite reasonable performance even in case of these buildings also. If we can take care of these irregularities, if the irregularities are within control. Okay. Any other question regarding hill buildings or otherwise?
So Suraj Gurung have asked a question, sir. Sir, in which case should we do non-linear pushover analysis and time history analysis?
Okay. When our building is not following the code. Okay. If you look at 16700 code, that specifies that in which case you have to go for nonlinear analysis. Otherwise, nonlinear analysis is not needed. If your building is following the code, then nonlinear analysis is not needed. Based on linear analysis itself, you can do it. Or if you are designing an important building and you want to achieve performance better than collapse prevention. Suppose you are designing a hospital and you want your hospital should be functional after the earthquake. Then you cannot design using linear method. Then you have to go for nonlinear method. Ordinary building, following the code, no need to go for time scale. No, sorry, this nonlinear analysis, pushover or time scale.
Okay.
Okay.
So if there are any other questions, participants can ask directly.
Okay, so I think they are finished with their questions.
Okay.
So one question.
Yeah.
How to connect the column with plinth and low tie beam?
Sorry, how to connect column with?
Plinth and low tie beam at the different level when we have to design in hilly area.
Then we cannot connect at the foundation level.
Means we don't need to have to connect the column with the beam in foundation level.
If it is causing a short column, then no. For example, let us take example. Then it will be clear. Suppose one column is here, another column is here, and when I am connecting this column to this column, okay, I have to see, okay, and there is another column. So I have to see that when I will be providing this beam, this column should not be a short column. Okay, if this will be a short column, then it will fail. How can I avoid this to be short column? By avoiding this beam. If this tie I am not connected, then I can avoid this to be a short column. Then it will be sufficiently tall. Okay, so it will depend on the actual flow, actual arrangement of the column. We have to not provide connections. I mean, we don't have to connect the plinth or the foundation in cases where it will give rise to short columns. Short columns are to be avoided.
Means it is only to provide at the plinth level only.
Sorry, it is only to provide
the beam at the plinth level only.
In plinth level also there may be a problem. Suppose you are continuing it here, then this column will become short column. So in that case, we will not provide this also. We will provide the beam here on the upper story only.
In that case, so it is quite different than the other which are found in the valley.
Yes, this arrangement has to be different than what we are following in plains. So the same configuration which we are following in plains should not be followed on hill buildings.
So can you please show me what will be the configuration of the detailing of beam and column in the hilly area? Just typical example.
So if you give me the slope and the placement of the columns, where you want to place the columns, then I can tell you, because it will vary from slope.
Okay.
If slope is milder and columns are far away, okay, then even if I'm joining this plinth, okay, the column will not become short column. Sorry, not plinth, foundation. I'm joining here, let us say. The columns are far away and it is not short column. Then you can join. In case of steep slope, even if the columns are relatively closer, you can see that it is not going to form short column. There you can provide. but here it may be short column. So in that case, you don't have to provide the connection. I mean, you have to avoid short column.
Sir,
Okay.
Somehow you have to avoid short column. That's it.
so there will be the possibility of formation of plastic hinging in that short column, that upper side.
The
And for
short
the,
column will fail in shear. We want to avoid failure of the columns in shear. That's it.
To avoid that short column effect, can we provide the shear wall in the direction of the slope?
Yes, we can provide shear wall. I mean, that can be one option, but foundation of the shear wall will be a challenging issue, because the shear wall is to be provided either like this in this shape, or it is to be provided like this. How you are going to provide shear wall, you have to think about it.
So there may be surely a lot of question and a lot of doubt, and we can always consolidate our question and send them as a bulk to sir. So I will preparing a Google form where you can ask your question, and some of the questions sir will answer. So right now we have time.
If you send your practical problem, then it will be easier for me to answer. Okay, so if you have a practical problem where you are facing some problem, just share with me. You can discuss it. Okay.
Okay. So I would like to request Mr. Dwarika Shrestha to give vote of thanks for this program. Mr. Dwarika Shrestha is a former Joint Secretary at Ministry of Urban Development and Joint Secretary Technical at National Reconstruction Authority Nepal. It is very glad that sir have come and attended this program. And now the task two is over to sir. Sir, can you please give vote of thanks for this program?
Thank you. Thank you. I would like to take this opportunity to express thanks to Dynamic Solutions for organizing this very interesting seminar. And also I would like to express special thanks to Professor Yogendra Singh, who provided us insights into different aspects of Indian Seismic Code, IS 1893 Part 1, as well as the Ductile Detailing Code, IS 13920. And in this webinar, we not only discuss about the various aspects of Indian Code, but he provided the comparison between the Indian Code as well as the newly published NBC 105 version 2016. Earlier, we were using previous version of NBC 105 1994 version, but because of the delay in revising the code, we were mostly using the Indian Code IS 1893 2002 version, and then the revised version 1893 Part 1 2016. And still, many of us have been extensively used that Indian Seismic Code IS 1893 Part 1 2016, but there are still many confusing parts which were discussed during this webinar. And at the same time, Professor Yogendra Singh provided us the comparison of different clauses of NBC 105 in comparison to the Indian Code. So I find that this webinar has been very useful to all of us, which provided us the opportunity to have clarifications on different clauses of Indian Code as well as Nepal Building Code also. At present, Department of Urban Development and Building Construction is working on preparing the guideline for using NBC 105 2016 as well as illustrative example also. So since this has recently been issued as a revised version of NBC 105 1994, many clauses of the NBC 105 are not very clear. So once the guideline and illustrative example is launched from DUDBC, many of the clauses will be clear to all of us. So even then, though it is still taking more time to issue the guideline as well as illustrative example from DUDBC, this webinar has given us opportunity to compare the clauses in NBC 105 against the similar clauses in IS 1893 Part 1 2016. So we hope that in the future also Dynamic Solutions will also come up with more such webinar related to earthquake resistant design and construction of building, as well as analysis of building for earthquake load. So at the end, I would again like to express thanks to Professor Yogendra Singh as well as Dynamic Solutions for giving us the opportunity to participate in the webinar and raise questions related to NBC 105 as well as IS 1893. Thank you very much.
Thank you, Mr. Sister. Okay, so we take leave, and we will be in touch. So please keep in touch. Whatever point you want to discuss, just write an email. I will try to respond to that. Thank you.
Thank you, sir. Thank you,
Bye
sir.
bye. Take care.
Thank you, sir.